worked very well, I think.
Amazing. And I suppose it beats jet lag.
So what's the weather like in Atlanta?
Having a problem.
It's cold, but not that cold.
Yeah, it's a lovely day here. I've had to back myself into a corner to avoid. You'll see some light there behind me. That's from the back, and if I turned any other way in this room, there's too much light from behind. So it's really a bright, nice bright day here.
It's been raining here the last few days, and but it's but I only hear about it. I don't go outside.
What's going on in Georgia?
Georgia has been the center of the universe for a while now.
Yeah,
right. That's right. Ptolemy was
They're learning mathematics these days. Now, you know, you count once, twice, 3 times. You start from the other side, 3, 4, 1, and
well, people in Georgia don't count well, so we have to do it many times.
It's the problem with mathematical literacy, no?
Yes. Yeah. You see, if you can't read, you're called illiterate. But people in Georgia are innumerate, which is the numerical equivalent of illiterate. Anyway.
Yeah, the state is changing, isn't it? Because it's becoming very urbanized, and they tend to be more liberal.
I mean, I have to say, I was amazed that Biden won here. Because a lot of Georgia is peopled with the finest minds of the 12th century, I would say.
You're always talking politics, even when they are celebrating your birthday. Hi, everybody.
Good morning, Alfred.
Good morning.
So the first one up is Eugene.
I checked in a short while ago to make sure I could share my screen, so I hope it'll work the second time, John.
Yeah, it should do. It's, I mean, all you have to do is press continue.
Yeah.
There and
How are you, John?
I think we're okay.
Good.
John, it seems that Roger Hutton is having some problem connecting once again.
I just sent him the.
That's okay.
The link I got.
Yeah, so I'm also replying to his concerns, and so is Devi Prashanti. So we are in touch with him, and we are trying to help him out.
Good.
Okay, there might be a fire. It sounds like a firewall or problem or something he has.
Hello.
Yeah, I have to say, Pranav, you did manage this transmission. It requires a lot of know-how.
Yeah, this is, and I myself so ignorant and very nervous about these things, but we have a very good technical team here, and they know how to do things. So they are the ones who are really running the whole program.
You know,
yeah, but you seem to be cool and know everything. I'd be nervous about things not working.
Well,
that's why I appreciate your coolness.
Yeah. Prano, you remember several years ago when we had a virtual group meeting there in India.
Yes.
And we had one or two people who were off-site, and the difficulties involved in the transmission up and back, and now it's like nothing.
Yes, it's.
I mean, this is one of the very few good things that the coronavirus has done for us. Everybody is at home, and at home you generally don't have firewalls like you do at the university. No, seriously, at many universities we couldn't do this because they use a different technology.
Yeah.
WebEx, for example.
Yeah.
And,
Yes.
You know, speaking of being
Roger.
at home, I told you I've known Steve for a long time. I used to go in the morning at his place. Around this time, I'd find him counting his money. And it's, you know, amazingly, he'd show me some of his most valuable stamps showing how much he trusted me.
Several others have joined now. It's good to see.
Okay.
We're getting there,
Good.
yeah.
Yeah, good to see a lot of people, right?
So
Okay,
we're
everything
about
seems
2
fine.
minutes to go.
Yeah,
Yeah, what about Roger? Is he there?
yeah, I'm here.
He's coming up
Yeah.
as John Costello.
A lot of people not here, but I'm here.
Oh, all right, that's good.
Hi.
Hi, Roger.
Oh,
Hi.
very nice. Yeah,
Yeah.
you had some technical problem joining the conference, I think.
Always, yes, always.
Yeah.
I've never opened Zoom without a technical problem.
Wow.
Partly because my computer, the software is in Chinese. So I don't know what it wants me to do. Oh, wait a minute. I'll be back in a minute.
All right. So
Guten Morgen, Horst.
I have to switch on my voice, yes.
Guten Morgen, Alfred.
Guten Tag.
Actually, it is
Actually, it's not
time.
good morning.
good afternoon.
Good afternoon.
Yes, 1
Good
o'clock.
morning.
You can say anything and it will be right for someone or the other. But it is time for our meeting to begin. So, John, are we ready to go? John
Yes.
and Anatoly?
I hope so. But Eugene is there, so we have the first
Yes.
speaker, which is good. So
Yeah.
it's a tight session with 9 talks. And so the last time I went to school, 920s was 180. So it's 180 minutes. I see Patrick Palmeri. Nice to see you.
Yes, nice to see you.
And so it's very tight. So we're on sort of 15 minutes. So I think at about 12 minutes, I'll do this and I'll say 3 minutes. So I will shout so you will hear me and I will say 3 minutes. And that will give us 5 minutes. And in the first talk, we'll try to see if we can get a question or two in and how that goes. If it looks like that's not working, then I think we should go to Anatoly's system, which is we put the questions in the chat and we just roll through the talks. And then I'll try to gather up all the questions and contact the speakers afterwards. But let's try to see, can we stick to 15 minutes and maybe 1 or 2 questions and then move over. Is that okay? Is everybody agreed on that? All right.
Whatever you decide.
Say again.
Whatever you decide. You are the man.
Okay, we try that. Well, let's try for the first talk. So, okay, so thanks everybody for joining. Happy birthday, Steve. I know we're a few days late saying that. But it's a great honor for me to chair this session, and I'm delighted with all the speakers accepted the invitation. We got no no's, which is great, and it's really amazing. Yuri is connecting there. So our first speaker is Eugene Kennedy, who's from this particular parish here. I've known Eugene a long time, and he gave me my job here. He hired me, so I owe him a lot. And so Eugene is, as you know, been very involved in atomic physics for a very long time, and more recently in molecular physics. And the title of his talk is Interaction of Short Wavelength Photons with Atomic and Molecular Ions, Some Examples. Over to you, Eugene.
Okay, John, thank you very much. So while I'm trying to share my screen with, let's see now, and I'll bring this up talk. Can you see that?
Yeah.
Yeah.
Okay, and I'll just move all of you a little bit to the side. Just to begin by thanking the Pranava and the whole team who are organizing this conference. It's worked very, very well up to now. So I hope I won't spoil that run. It's a great honor, as John said, to be involved with this, to recognize Steve Manson's very long and the distinguished contributions. So it's my first venture into Zoom world in terms of making a presentation, so I hope it goes okay. Let's see now how it, okay, the next slide just shows two things. The talk is divided really into two. Steve, of course, goes back to the swinging 60s. I'll not be going back quite that far, but I will be to the 70s. I'll describe briefly two joint papers with Steve. One as an example of results arising from a dual laser plasma technique and the other from synchrotron. And the second part of my talk will be to do with small molecular ions that we studied lately at Sole. And a theme throughout the talk will be, and I think Steve mentioned this on the first day, the symbiosis between theory and experiment. Experimentalists really do require theoretical support. So what I did was, at the beginning, when I was preparing for the talk, I went back to Steve's online CV, which I found, where he has listed all his publications numbered in order from 66. And the first one was in 66 on auto-ionization, but the first one with where I saw positive ions of atomic oxygen come up for any ions indeed, was number 17 and 72 on. Throughout the 70s, you can see a whole range, including Nobel gas isoelectronic sequence, mentioning highly stripped atomic ions, relativistic calculation. But the one I want to draw your attention to is the bottom one here. Photoabsorption cross sections for positive ions with Z less than 30. And I showed the first page of that on this slide here. And I just wanted to draw your attention to the first paragraph. A knowledge of photoabsorption cross sections for low Z positive is of importance in solar physics and astrophysics. In this range, photoionization, photoabsorption are essentially synonymous. Then he mentions experimentally very little is known. He mentions the results of Lucatarta and McElrath with a resonant laser-driven ionization technique on lithium plus and sodium plus, and another single point. And then he talks about some calculations, but he mentions the need for theoretical calculations. So coincidentally, in Dublin at the time, we were examining the output of laser plasmas, and we found that if we used the right targets, we could get very pure continua. And for example, this one shows, this was back when we used angstroms, 60 to 100 angstrom region. And this shows the actual giant resonance of xenon, which we just filled the spectrometer with, showing that we could do photoabsorption spectroscopy, a smooth, broad continuum. To do interaction of photons with ions, we need a good backlighting source. And so if I click the photographic plates, great things in terms of spectral coverage, but very poor indeed for time. You didn't know what you got until well after the experiment. And now the principle of what we developed, the dual laser plasma technique, is very simple. We have a backlighter continuum emitting plasma, and we produce the absorbing ions with a second laser fired before this one. And we can vary the density, power density on the target. We can vary the distance of the optic axis from the absorbing target, and we can vary the time delays. So we have a lot of control of how we produce this ion. And this continuum then passes through this, and we get a Beer-Lambert absorption. So this is the cross section. And so the cross section is given if we take the background divided by the transmitted intensity and take the log. And this was a very useful technique for looking at a wide range of ions. This shows the apparatus that we developed in the early 90s. This is the laser interaction chamber. So we produced the two plasmas here. This is a toroidal mirror chamber to couple the point-like continuum source into the slit of the spectrometer. Here's the grating holder. And then going along the rolling circle, we've got a microchannel plate backed with a photodiode array. And this has some of the properties of photographic plate in the sense that it has a broad spectral coverage at any particular setting. We can move it along to cover the whole range. But of course, one of the big advantages of this was that we had single shot sensitivity. So we saw the actual absorption spectrum on each and every single shot, and that helped us greatly to, if you like, optimize the absorbing species. The other fact that it's lab-based, so we could go in every day and refine the results and check things, unlike going to a synchrotron where you have a limited beam time. And this was enabled by European Research Network funding, as I said, in the early 90s. So the first paper I want to briefly describe is the combined experimental theoretical study. You'll see Steve here, but you also see Hidrami and Pranava. And this was looking at the photonization cross-section of the neon isoelectronic sequence, which we experimentally had found to have an unusual behavior at silicon 4+. So here's the calculations, the theoretical calculations using a 5-channel and a 7-channel approach. And you'll see the 5-channel, and maybe if I click this, I'll show it even more clear here. The solid curve is a result of 5-channel calculation, relativistic random phase approximation. And this is the 7-channel one. And you'll notice here a very low value for silicon 4+, completely out of the normal run. And this is because switching on these 2 extra channels brings in the subshell 2s to 3p excitation, which moves through down closer to the limit as we move through the series. And it was while we were writing up this paper that I had my first visit to Steve. So this is more clearly seen in this one, which shows the theory on the left. Here's the photonization limit, and you can see very smooth cross-section along here. You can see a rising a bit in magnesium 2+, because this is the 2s 3p, which is out here somewhere. Then in aluminium 3+, the 2s to 3p moves to here. Silicon 4+, it straddles the photonization limit. And in phosphorus 5+, it has moved to the left, and this is the 2s 4p. And here's the experimental results carried out by Andy Gray, our PhD student at the time. So you have the ND series, for example, leading to a fairly smooth limit in all of these cases, but look in silicon 4+, a very radical difference near the cross section, near the limit. So I just reproduce here the conclusion because it shows the value of Steve and Pranava and Hidrami's input. The theory agrees with the experiment about a dramatic anomaly at silicon 4+, associated with moving inner shell resonances. But from the specific case of silicon 4+, it's now further pointed out this should be a general phenomenon throughout the periodic system. And so this is the value of theory, that it's enabled to generalize from the specific case. The second one was a synchrotron experiment carried out in France at the Super Echo synchrotron facility on a merged photon beam developed by Bizot, Cubain, and the Volumia group. And in this, again, you'll see the Atlanta-Madras axis. Here we measure silicon 2+, and are able to put it on an absolute cross-section basis, as Alfred described yesterday in his very nice talk. So here we have this single and doubly ionized channels with the doubly ionized switching in here. And a point I want to make about this is that we had prior experiments with the dual laser plasma. When you go to a synchrotron, you have to scan. And so it's always good to know where to look. So we had prior data, and in particular, we had prior data on this very weak features down here around 95 EV, because these are due to metastable transitions. And we were able to quantify the metastable contribution as about 3%. Now, these metastables are there in a lot of these experiments, and oftentimes the only way we can estimate the fraction is through comparing theory and the experiment, which is not a completely satisfactory way of doing it. So if I look at some of the advantages of dual laser plasma, very versatile, you can use for isoelectronic sequences, and we've been using it for a good many years. But we're all very much aware of the dedicated online developments as storage rings. And here, the first absolute cross sections measured in the 80s, at Orsay, developing back into the current system, the current facility, Soleil, covering this range. I mentioned in particular the advanced light source, which covered a lot of atomic ion stuff. the most recent and state-of-the-art pipe facility at Petra 3, covering a very wide spectral range with a very long interaction length and very high photon brightness. So I particularly talk about this complementary nature. It's very good to have some DLP work done before you go to the synchrotron. But photonization studies of small molecular ions, despite their fundamental importance, are still rather scarce. A lot has been done with the atomic ions. And one of the reasons for this is increased complexity for experiment and theory. So here are some past results of small molecular ions, Anderson and co-workers at Astrid, and then at DLS, and some very nice fragmentation studies at the free electron lasers. What I want to describe now fairly quickly are the K-edge and L-edge photonization for small molecular ions. We're going from the single atom upwards rather than for the very, very heavy molecules as described by Alfred yesterday. So these were carried out at Sole. Here's the Maya apparatus, multi-analysis ion apparatus, and installed by Jean-Marc Bizot, Denis Cabane, and François Valoumier. Excellent energy resolution. We can have ion stage selection and absolute cross sections. So here's the principle, and this was shown again by Alfred yesterday. You've got an ion source, an ECR in this case. You select the ion that you want to study, and you bring it in to this interaction region via some bending magnets, where it's overlapped with the monochromator undulator photons coming in this direction. So you've got an interaction region. The photo ions that are produced here are then selected here so that you can look at each resulting ion in sequence. Now, the problem with molecules is that molecules dissociate. So for example, if you were trying to study, say, N2 plus here, if one nitrogen goes one way, the other nitrogen will go the other way, and you won't be able to capture them well. In our case, sorry, okay. In our case, we get away with it because of the mass difference between silicon and the hydrogens. So this shows the evolution in the series. And so we start from the bare ion, silicon plus, and we add each hydrogen in sequence. And you can see a rather nice trend of moving towards lower energies due to the additional screening of the additional electrons. They were all measured in silicon 2+ channel, and they were normalized up here at about 120 eV to put these on a cross section, assuming that the cross section for ionization at these energies is the same in all cases. And we had previously measured the absolute. Here is the theory versus experiment, and we were thankful to Stefan Carniato and his colleagues for this. And it gives insight into different regimes and geometries. So if you look down here, you see a broad, shallow region due to strongly dissociating states. Excuse me. Then you've got a valence excitation regime and a whole Rydbergs. And this is more or less replicated in all three species. They produce ab initio singlet and triplet, so ground state and excited state, and then they optimize the mix to best replicate the experiment. And I suppose one can say that the contributions show that we need metastables to show the agreement. The overall shape of qualitative are produced, but not the details. But when we integrate over the whole spectral region, there's fairly good agreement between experiment and theory for all species. So this was a case of the experiment, if you like, getting the theorist to work. There was a nice turn in the story, however, because theory predicted there should be other structures down at shorter, lower energies. And in a subsequent meantime, Jean-Marc and Denis found some structures down here in SiH2+, which I'll show magnified now. And this shows vibrational structures. Again, the theorists got to work, and they found out which states were primarily producing this, and this is the best, the optimized mix, and the agreement is quite good. But what I liked about this was the theory predicted this in advance of the experiment.
1
My
minute.
last
50.
example is K shell for CH plus and OH plus. Again, we made the absolute measurements for the bare atomic ions on the same apparatus at the same time with the same bandwidth. Here's the experiment and the theory. The structures are simpler in this case. You've got the strong 1s/2p equivalence here, and you've got Rydberg's up here. So overall, the agreement there is fairly good, although there are still differences in terms of cross-section. So if I was to summarize, photonization of atomic ions is a reasonably mature field, particularly with the onset of the pipe facility now at Petra 3. Small molecular ions, I've described these few cases here. We've also published a paper which is primarily theoretical on NH+. A lot of results from Petra and the ALS here. The first three are for the small molecules, INH plus at the 3D iodine threshold, and then NHY plus and CHXI plus. And of course, we heard a lot about the fullerenes yesterday. But still relatively early days, I think, for small molecular ions. And of course, theory and experiment will be key. So just to finish up with a few pictures, Steve, this shows you, me, and I think Finn Folkman here at the highly charged ion conference in Belfast when you visited Ireland, and again in Belfast a few years later at the ICPEAK. You're there in the foreground. This shows a picture I got from Valery Dalmatov to remind people of Stone Mountain, because I had a very nice visit there with you and Betty, but I didn't take any pictures at the time. So this gives a feeling of the atmosphere, and our conference chairman is also there. This is a picture I did take when I was last visited you in 2014. And it shows your publications up on the board, very impressive at the time. So for this talk, I did a Web of Science search, and these are your publications per annum. And I just point out two very strong resonances here at 75 and 80. So a question for Steve is, can he explain the Y equal to 75 and Y equal to 80 resonances? Finally, my thanks to Steve and the Mesras team for collaborations and enjoyable interactions over the years. For the dual laser plasma work at DCU, my colleagues, John, of course, Jean-Paul Mosnier, Paul Van Kampen, and all the members of the DCU group, including all the PhD students in particular over the years. I also mentioned Bernd Sonntag here because he was a key member of the European Research Network that enabled us to install that facility at DCU. Synchrotron, my colleague Jean-Paul Mosnier and myself have visited on several occasions now and joined the group of Jean-Marc Bizot, Denis Cobain, and so. Recent theory, Christoph Blanker, Brendan McLaughlin for atomic ions, and we have Stefan, Alessandra, and Nicholas for the molecular ions. I finally finish with a picture which I hope, Steve, you'll like. It shows Denis, Jean-Marc, and Jean-Paul at Sole. You'll notice they all have drinks, bottles of water in their hands. So I take this as a virtual representation of us all raising our glasses to you, Steve, and to wish you a very, very happy birthday indeed. And thank you all for listening, and stay safe, everyone.
Thanks, Eugene. We're tight on time. We probably have time for just one very quick 20-second comment if anybody has one.
Oh.
No. Okay, if not, if you can put your questions in the chat. And thanks to Eugene. I mean, I think it shows the moving from atoms to small molecular ions is the way to go, because one can see the transition and probably make it more tractable for theory. So our next speaker is Nobuyuki Nakamura. Nakamura-san, you're there. I see you. Hi, welcome. And so from the University of Electrocommunications in Tokyo in Japan. And Nakamura-san will talk about bright interaction effects on recombination processes of highly charged ions. Over to you.
Thank you, John-san. I am Nobuyuki Nakamura from the University of Electrocommunications, Tokyo, Japan. Today, I would like to briefly review the studies for the Breit interaction effects on recombination processes of highly charged ions. First of all, I would like to thank the organizers for giving me this opportunity to give a talk at this special meeting for celebrating Professor Manson's 80th birthday. This is a paper by Manson Sensei studying photoionization of highly charged ions. This is a result for the ionization cross-section of aluminum 6+. And over the nearly flat structure from the direct ionization, we can see many structures arising from resonance ionization. So it should be very interesting if we could study such processes for more and more highly charged ions such as hydrogen-like, helium-like, lithium-like, for example, bismuth, uranium, or so. However, it is practically difficult to observe such processes for few electron-heavy ions. What can we do then? Is there anything we can do? Yes, we can study the inverse processes shown here. This process is called radiative recombination, and this is the resonance recombination known as dielectronic recombination. Here I am showing those processes schematically. In radiative recombination, the incident electron is captured into highly charged ion while emitting excess energy as an X-ray photon. On the other hand, in the dielectronic recombination DR, excess energy is used to excite an inner shell electron. Finally, this inner shell excited state is generally stabilized by emitting an X-ray photon in the case of few electron-heavy ions, because the fluorescence yield is almost unity for the heavy ions. The DR is resonance process that can be realized only when the excess energy coincides with the excitation energy of the inner shell electron, whereas RR can be realized at any electron energy. And the powerful device for studying such processes of highly charged heavy ions is an electron beam ion trap, EBIT. Here I am showing the principle of an EBIT. Here, simply speaking, an EBIT consists of a penning-like trap and a high-energy electron beam going through the trap. Highly charged ions are produced through successive electron impact ionization by the high-energy, high-density electron beam compressed by a strong magnetic field produced by superconducting magnet. The produced ions can be stored in the trap for many hours, and the radiation from the trap ion can be observed through the observation slits opened in the middle of the trap. This is the picture of our EBIT called Tokyo EBIT. The electron beam travels vertically from the bottom to the upper direction. The ion trap shown, our trap shown here is located in the middle of the trap around here. This is the middle of the trap where the highly charged ions are stored. From these slits, we can observe the radiation from the trapped highly charged ion. And this slide shows the typical experimental procedure for studying DR through X-ray observation. In this method, the electron beam energy is swept by changing the potential at the ion trap. X-rays emitted from highly charged ion is generally observed by a germanium detector at 90 degrees with respect to the electron beam. The X-ray spectrum is thus recorded as a function of electron energy, as I will show you in the next slide. This is an example of X-ray spectra obtained for bismuth ions while sweeping the electron energy from about 50 to 60 kD. The vertical axis is X-ray energy. The intensity of X-ray is shown by this color bar. And these diagonal lines correspond to RR, radiative recombination, as the X-ray energy increases with electron energy. On the other hand, these bright spots correspond to DR, as the X-ray intensity is enhanced only at their resonance energy. In this energy range, KLL resonances are observed, where K shell electron is excited to L shell while capturing the incidental electron to L shell. According to the fine structure of the L shell, in this region, the mainly three parts. It is divided into three parts: KL1212, KL12L3, KL3L3. Since several charge states exist in the trap at the same time, their resonances from the several charge states observed at the same time. And another method for measuring DR is to observe ion abundance in the trap as a function of electron energy. In this method, ion abundance in the trap is measured by charge analyzing the extracted ions. And the DR can be observed as a sharp increment, sharp change of abundance at resonance energy as shown in the next slide. And this is an example of ion abundance ratio measurement performed for bismuth ion. Here, ion number ratio between the beryllium-like to lithium-like is shown as a function of electron beam energy. And the sharp increment observed here of the beryllium-like ion with respect to the lithium-like ion correspond to DR of the lithium-like ion. Here I am showing the comparison with the two different theoretical DR cross-sections. And the blue one is calculated by considering the Coulomb interaction only, whereas red one is calculated by taking the Breit interaction into account. What is the Breit interaction? The potential of interacting electron can be written as shown here. In addition to the non-relativistic Coulomb term, the magnetic interaction and the retardation should be taken into account as a relativistic and quantum electrodynamics effect. And these terms are called Breit interaction. And it is the Breit interaction is generally important for highly charged heavy ions, but the Coulomb term is generally so large that the Breit interaction is only small correction to the Coulomb term, even for heavy charged heavy ions. The situation is very similar to the energy levels, where the relativistic and the QED effects appear as a small shift or split. However, as you can see, the Breit interaction affects the strength of this resonance very strongly. The strength is almost twice compared to that without Breit interaction. The calculation with the Breit interaction reproduce the experimental results quite well. This shows the atomic number dependence of the resonance strength of this resonance. The experimental results shown in black squares shows strong atomic number dependence. And the comparison with the theories with and without Breit interaction has demonstrated the significant Breit interaction effects. And later on, Stefan Fritz-san and Andrei Srivkov-san showed that the Breit interaction can strongly affect not only the resonance strength, but also the angular distribution of X-rays emitted in DR. And this shows the angular distribution for the atomic numbers 53, 67, and 83. When only the Coulomb interaction is considered, the distribution has a minimum at 90 degrees for all of them. On the other hand, when the Breit interaction is included, the distribution has a maximum at 90 degrees for heavy elements such as bismuth. The angular distribution can also be represented by so-called alignment parameter defined in this equation. And this plot shows the atomic number dependence of alignment parameter. The dominance contribution of the Breit interaction is predicted as shown here. However, unfortunately, our EBIT has observation ports only at 90 degrees with respect to the electron beam, so that we cannot observe the angular distribution. Alternatively, we combine two experiments, X-ray measurement and the ion abundance measurements, in order to obtain angular distribution. From the X-ray observation at 90 degrees, we obtain differential cross-section. On the other hand, from the ion abundance measurement, we can obtain integrated cross-section. Thus, the combination of these two experiments tells us the angular distribution. As a result, we could demonstrate the dominant Breit interaction effect on the angular distribution as shown here. And this shows the result only for gold element, but later on, we also demonstrated the atomic number dependence in this paper. And the angular distribution is identical in physics to the polarization, which can also be represented by the alignment parameter as shown here. And Jose and his colleagues made an excellent experiment with an EBIT in Heidelberg to determine polarization. They used a polarimeter based on compton scattering. From the modulation in the azimuthal angular distribution of the scattered X-rays, they obtained the polarization precisely as shown here. You can see there are small error bars compared with our angular distribution measurements. And very recently, my Chinese colleagues, Qiming Hu, Shangao, and Kao found another interesting aspect of the Breit interaction effect. The Breit interaction is the interaction between two electrons, so it is generally considered to have little contribution to radiative processes, because only one in the radiative decay, only one electron makes the transition. And contrary to this general understanding, they found that the transition rate can be strongly affected by the Breit interaction. They study the transition from this inertial excited state of boron-like ions produced by dielectronic capture into beryllium-like ions. It has two decay channels. One is to 1/2 transition 1, another is to 3/2 transition 2. And this shows the ratio between these two decay passes as a function of atomic number. The blue and red curves are theoretical values without and with Breit interaction, respectively. Significant Breit interaction effect is found, as you can see, and the experimental value plotted by black circle show good agreement with the value with the Breit interaction. Okay, this is the final slide, and let me explain the mechanism of this very interesting phenomenon. The initial state of the transition has an angular momentum of 3/2, and it can be represented as the linear combination of these two states that have different angular momentum for the 1s2p core. Out of these two states, the former cannot decay to 3/2 because it involves 0-to-0 transition in the core. Thus, the mixing coefficient plays an important role in the radiative transition rate. And this panel shows the theoretical mixing coefficient. The red and blue ones are the results with and without Breit interaction, respectively. Here you can see that the Breit interaction strongly affects the mixing coefficient. As a result, the Breit interaction can change the nature of initial state from the state 2 to state 1 as the atomic number increases. And the transition 1 becomes dominant for higher atomic number. Why can the Breit interaction affect the mixing coefficient as shown here? It is because the Breit interaction is responsible for the avoided crossing realized between these states as shown in this panel. This crossing appears only when the Breit interaction is considered as shown here. Unfortunately, I don't have enough time to explain the details, so please visit this archive paper and this theoretical paper are published recently. Okay, let me summarize my talk. Breit interaction can play a significant or even dominant role in the collisional and the radiative processes of highly charged ions. And an electron beam ion trap is a powerful device for observing such processes. Now let me show you my collaborators for these studies. Kato-san, Watanabe-san, Ton-san, Gao-san, Fu-san, Yao-san, Lee-san. Okay, thank you for your attention.
Thank you very much, Nobuyuki. So do we have a few minutes. So do we have a quick question or a comment from anybody? No? Could I ask a quick question, which is, so on the calculations, I take it they're Dirac-Hartree-Fock calculations that somebody is doing, is that correct?
Sorry?
So in calculating these mixing coefficients, the calculations are done using something like the Dirac-Hartree-Fock package, one of those programs.
Sorry, I don't know the detail, but the Gao-san made the calculation.
So he's doing the calculations.
Yeah.
Yeah, no, because it's quite dramatic with and without. Are there any other comments? No, if not, thank you very much.
Thank you very much.
And thank you very much. And we move on to the next speaker. The next speaker is Roger Hutton from Fudan University in Shanghai. Are you there, Roger?
I am.
Hello, excellent.
So,
are you able to share your screen?
Yes.
So the title of Roger's talk is Measurements of Active Region Magnetic Field of the Solar Corona Using Spectral Lines of Iron 10. Over to you, Roger.
Thank you. I'll just try to work out how to start the slideshow. Here we go.
There you go.
Okay. Okay. So I'm going to talk about something totally different from what you've heard about so far, which is the solar corona and its magnetic field. And I'll start by thanking John very much for this interesting invitation, and also thank our Indian friends for putting up with many questions from me about what time of day it is. I still don't know what a CTU is. Anyway, my Chinese name is given there if anybody's interested, Lord Jia, and I'm from Fudan University in China. So what I'm going to be talking about is basically this spectrum here, which is recorded by a satellite called Hinode, which has been operating since about 2007, taking spectra like this of our sun, our solar corona. And I'll be concentrating on a line, especially at around 257 angstrom. And people have seen that line since 2007, actually seen it before, and no one has known the significance of it. It's actually really very, very significant. Well, my collaborators are people I've worked with for many years, except for a new collaborator here, Enrico Landi, who knows Hinode extremely well. He also knows the Shanti database, which we've been using, as he was one of the instigators of that collaboration, and also a man from the Chinese Academy of Space Instrumentation, who's very interested in the results, because he might like to send something into space to measure what we're predicting. So I'm looking at this thing here. It's our sun, but the picture is not taken with a visible camera, obviously. It's taken with an X-ray camera. So all you see are photons coming in the X-ray, which usually means highly charged ions, as was shown by Bengt Hedlund in the 1940s. You have a very bright part here, which is a solar flare. And I wondered I asked an astronomer once, what's the energy released in the solar flare? And he said, 10 to the 31 ergs. And I said, what is that? And to break it down into a unit you still cannot understand, it's equivalent to 1 billion nuclear weapons exploded over a 20-minute period. That's the kind of energy released in a solar flare. And I'm going to talk about atomic physics as well. And if you look here, we have a atomic structure of neon-like, in this case, argon. And we have a transition here from triplet P0 to the singlet S0, which, if you know any atomic structure, you know is totally forbidden. This cannot occur under the condition of a single photon emission. The rest of the structure is quite well known. The triplet P1 being the 3F, then you have the 3G and the M2 line. What about the spectral? Well, there it is. You have the B line there, which is a triplet P0 decaying to a singlet S0. This spectrum had been seen many, many, many times, but never had anyone seen the B line, because the B line depends on magnetic field. Not only is Zeeman quenching, but hence broadening, but also you have a quenching of the upper level, giving a decay here, which cannot happen without a magnetic field. We call this extra line a magnetic induced transition, MIT. These are actually very new for atomic spectroscopy. This first one here was 2003. And it was induced by mixing of these two levels here, the triplet P0 with the singlet P1. The magnetic field can induce mixing between levels of the same parity, a mix of differing J by 1 unit. But this mixing required a field of about a Tesla, and therefore this research was stopped because there's nowhere in astrophysics, well there is, but they're difficult, but our solar corona does not have a field of 1 Tesla. So nothing really happened. An interesting question is, how can we study the solar corona in our laboratory? And you just heard about electron beam ion traps from Nakamura-san. We have 3 in Photon, a high energy one, a permanent magnet one, and also a high temperature superconducting one. Sometimes they call this a solar flare laboratory. And this is the one we've done. The only experiment so far that we've done on the stuff I'm going to talk about was done using this EBIT here. Again, back to the solar magnetic field. Solar magnetic fields, they cause actually or one of the underlying causes behind solar flares and space weather. Space weather is a phenomenon caused by our sun's activity. Main solar events responsible for space weather are solar flares and the coronal mass ejection, which I just showed you, resulting from the flare. They also give us those rather nice colors we call the northern lights, or if you live in Argentina, they're probably called the southern lights. An underlying cause behind solar events is the conversion of magnetic energy to thermal energy. I don't know anything about this, astronomy told me that, but it's very, very interesting. There's no way to measure the strength of the solar corona magnetic field. After hundreds of years of studying the solar corona, the first spectrum was taken 1857, I think, we still have no way to measure the magnetic field. And after studies of atomic structure of highly charged ions, we've recently proposed a method to measure this magnetic field strength. Not only proposed, we've actually done it now. We need atomic structure sensitive to the magnetic field of corona importance, not of, these mean hundreds of Gauss, not of Tesla. So we need a system with a small fine structure, and I'll tell you what else you need in a minute. We need two levels for most diagnostics. One with allowed decay to the ground state and one without one. And we have an accidental genus here. This was very interesting, that you have a system here in iron 9 plus or iron 10. The ground configuration is the 3p squared WP, 2 levels here. And then we don't worry about this configuration here, but then you have the 3s squared 3p4 3d as a coordinate d. This is the lowest term in this configuration. Oops, what happened? Head back. And you have a coordinate 7/2 as the lowest level, 5/2 as the next, and you have a 3/2 and a 1/2. What we knew before we started our study is that these two interchange. If you look in this database, if you can find any data, at some stage of the 5/2 is below the 7.5. Therefore, you know at some stage these two will cross. Based on Zeeman quenching of this 7.5 level, even by a weak magnetic field, this depends now on the fine structure, you will get an MIT, a magnet-induced transition. The ground state, the M1 here, actually gives rise to a very strong visible line. It's called the corona red line. And this tells us that ion 9+ is a very abundant charge state in the corona. This is also important. This is published in this paper here. We really do need to know what is this delta E, because I'm showing you the formula above, which tells you the MIT depends on, I cannot see it myself, it depends on B squared divided by the product of the wavelength cubed times the fine structure energy squared. And we know the wavelength very, very well. We know it to 3 decimal places. We need to know delta E, and if we know delta E, we measure the MIT rate, we can then extract what is the field strength. How to measure this delta E, this is a bit awkward. The most straightforward would be to observe 2 spectral lines, but there was an astrophysical estimate of this delta E of 5 centimeters to -1, and that would require a spectral resolution of 80,000, which is, believe me, difficult. There are 2 spectrons in the world, they're 10 meters long. They can get this resolution, but they don't have low density light sources. And where you have low density light sources, you do not have spectrometers with 80,000 resolution. So we need an indirect measurement. And we used our EBIT because, as I've said, the MIT, the magnetic induced transition intensity, is proportional to the magnetic field squared divided by the product of the wavelengths and the fine structure. But if I know B, which I do in an EBIT, I know what B is. Therefore, if I measure the MIT intensity in ratio to some other line in ion 10, I can extract what is the delta E. And this is what we've done here. You can see the red part here is the blended transition. It's actually a blend between these two here, the 7.5 and the 5.5. We cannot ever resolve those two. So you call that the blend, and then the line from the 3.5 down to the ground state is what we call the 6:1 line there. So we can measure this ratio, and from that ratio, we can extract a value for the fine structure, and we did that, and we get 3.5 centimeters -1. Sadly, the error bar is also 3.5 centimeters -1. So roughly, we don't have a decent measurement, but okay, that's what we got at the time. Wait a minute. My screen's going crazy. Okay, we then made another measurement, 2016, using spectral lines from a doublet G7.5, which is in the same 3P43D term configuration, having 2 transitions into the 2 quartet D levels. And we got fine structure 3.6 ±2.7. This is from data from a spectrometer on board a thing called the Skylab in the 1970s. Very, very nice spectra you have from this machine here. And finally, this year, we made another measurement. This is where Enrico Landi came into our collaboration. He made a new measurement. There we have 2.2 ±0.5, 22%. You've seen the formula. And you can see the error in the magnetic field is basically directly proportional to the error in the fine structure energy. Therefore, if we have 100% fine structure energy error, we have 100% in MIT, and no one's interested in that. Now we're down to 22%, and it's getting so you could start thinking about actually using this. We did a lot of calculations, obviously, don't just come to the idea that ion 10 is the most useful element. So we did calculations of the fine structure along the isoelectronic sequence. As I said, they change order for some ion along the sequence, and we did not know where, but it is, if you look, it's in iron. So if it had been anywhere else, if it had been here or been here, this measurement would not be useful. It happens to be an ion, and happens to be an ion 9 plus, which is very, very abundant in our universe, in our solar corona. And well, very lucky that the minimum fine structure energy is for a chlorine-like ion. And this ion is abundant in the corona. And as my PhD supervisor used to like to tell me, it's a lot better to be lucky than to be smart. And we're very, very lucky. This is now looking at the...
2 minutes, Roger.
Yeah, 2 minutes, yeah, I'm almost there. Looking at data, this is our EBIT data at the bottom compared to the Hinode data. And you can see the line ratio is wrong. The small one in the blue is the 6:1 line, yet that is sadly a big line in the Hinode data because it's blended by helium. But so we can use other lines. We use a normalization from other levels in the same configuration. So we use lines at 174 and 175. And we published this with a rather large error bar, as I've told you. And then we, working with Enrico Landi with our new 2.2 plus or minus 0.5, 22% fine structure measurement. This is just simulations of the lines we use using Chianti, just to show they're actually unblended. That's an also important point, that the lines we actually use in this measurement are not blended by anything. And now I'll show you, this is the measurement we made with the 3.6 plus or minus 2.7. The gray area is the error bar introduced mainly by the fine structure energy. And then my last slide, it almost seems a bit of an anticlimax. And there is a map of the magnetic field over the solar corona in 2 different directions. And the brightness indicates the strength of the field. And it's a working measurement. This work is described in detail in this paper, if you like to read it. We haven't finished because we need to know this fine structure better. And I don't know how to do that. And we also need better calibration of the EIS instrument aboard the Hinode. And we're encouraging atomic physics community to improve the collision data. We have also already done a benchmark atomic data for this magnetic field induced MIT. We've done large scale calculations, and we've presented what we believe are the best values for the atomic structure here. And then just to show there is life in this field of atomic spectroscopy. Sometimes you think we're all dying out and we're only people like me. But last summer in June, we held a thing called ASOS, Atomic Structure and Oscillator Strengths, in Fudan. It will be held in Paris in 2022 in the spring, if we're lucky. But what's very nice about this picture is the front line. They're all young people. There's a lot of young people involved in atomic structure, mainly through calculation, I know, but still, it's very, very encouraging. So, thank you. That was it. I've lost my last slide. We just said thank you.
Okay,
Thank you.
Roger. You're actually very, very well on time, and that's a very important note to end on. Actually, to show that there's still life left in atomic physics and in highly charged lines. So, are there any comments or questions from anybody on the talk? So. Let me ask a quick question as we have a little bit of time. So 80,000 as a resolution.
Yes.
And you mentioned the difficulty, and there, some of us can get to those resolutions, but the problem is the light source. Is it the weakness of the source?
Yes. It has to be an EBIT.
Okay. Well, then you're kind of photon counting on.
Yeah. Actually, okay. I didn't tell. There is an easy method. And that is the one used with the line coming in from the doublet G at 1603 angstrom. And because you filed it out from the 257, the resolution goes down to about 20,000. Okay. That is a doable experiment. That's very close to being possible to do.
Yeah, no, we all know the difficulty working with EBITs. I don't know it personally, but I have lots of colleagues in UCD and elsewhere will tell you about how long it takes. And I've visited you a few times in Shanghai
okay.
to see your EBIT, and yeah, they're not easy experiments. We're probably about to hear about in the next talk. Thank you, Roger. Much appreciated.
Okay.
We're probably about to hear a little bit more about the difficulty of working with highly charged ions from the next speaker. So the next speaker comes from MPI. Are you there, Jose? Hello. Have we lost Jose? Hello. Oh, you're there.
Yes, the internet is crazy. I hope everything works.
Okay.
So
our
I'm
next
supposed to talk now.
Jose Crespo from MPIK in Heidelberg in Germany. Complex photo recombination and line formation in highly charged ions. Over to you, Jose.
Okay, thank you very much. I hope everyone can see this. I have to find the spotlight here. Yes, okay. So I will talk about, many thanks for the invitation. It's great to be invited here and to speak in honor of Steve and his birthday, and to see many old friends. What you see there is a complex photorecombination pattern, and I am thankful to Nakamura-san, who has explained things very well. So I will try to show you what we are doing here. The F iron L shell photoabsorption is essential for the opacity of the sun, and there are millions of resonances there, and this complex set of resonances actually carries out, if you fold it with the Planck continuum, most of the photoabsorption width. So you can ignore the direct channels because the indirect channels are really dominant there. And this is very important to understand them better and to measure them. And, you know, we use EBITs, we have an electron beam and we produce the highly charged ions, and we put detectors and we look at them, and it is a very, very useful tool for that. And the classical EBIT experiment, as Nobuyuki explained, is you have your detector on the side. Sorry, I have to go back. You have your detector on the side, and you change the electron beam energy, and you observe the energy of the photons which are emitted with your germanium detector or your silicon drift detector, and you see the beautiful resonances coming up. And then one remembers that all this happens simultaneously in a plasma, but in an EBIT you can kind of unfold it. And what we saw in some EBIT experiments is when we improve the resolution, that this dielectronic recombination is also complemented by a tri-electronic and quadroelectronic recombination process, where basically L shell electrons are co-excited when an electron, a free electron, is captured. And these tri-electronic and quadroelectronic recombination processes actually have a sizable contribution in elements like iron, argon, and neon. Then we looked in detail by enhancing the resolution as we scan the electron beam energy. This is now the K alpha emission of iron. And we are looking with two different detectors in different aligned positions at 90 degrees and at 0 degrees. And by doing so and going into the resolved resonances, we can determine also their alignment and polarization. And this is what you see here, the intensity at 90 degrees compared minus the intensity at 0 degrees. And you see that certain resonances, in particular, some of the tri-electronic resonances have strong polarization effects, and they have to be taken into account. So this is what you see when you look at high resolution into the KLL recombination spectra of iron. We are thankful for theory, because theory is the only thing you can have in order to put names to all the transitions that you see there, and to tell if they are quadroelectronic or three-electronic, and so on. So we resolve them and we compare them with different theories and so on. But things can become more complicated if you involve the L shell and the M shell. There are many other excitation channels, resonant electron scattering, resonant inelastic scattering, photo emission recombination. Much of this is analogous with what happened in the Auger studies. And this is the map which I showed you at the beginning. This is actually the iron LMM structure. So we are scanning the electron beam energy here from 300 eV to 1.2 kilo electron volts. I'm observing photons around 800 electron volts and higher. And there is a big, big, big mess. And if you zoom into a region, you can see indeed a lot of resonances. And it is simply not sufficient time here to go into the details. But it helps to have high resolution in the experiment. These you reach by evaporative cooling in EBITs and by doing the scans slowly and fast, depending on the conditions. And you can learn quite a bit, many things about these photorecombination processes. What is perhaps also interesting, we show here an experiment which was carried out of the TSR storage ring in Heidelberg. So this is this data point. And this is basically a recombination in the storage ring. And the blue curve is recombination theory, and our experiment is the black curve. So in the storage ring, you are not observing the photons. In the storage ring, you are observing the recombined ions, but they overlap very nicely in the region where they have common energies. We have to fold the data from the storage ring with a factor of 3, make them broader because they were indeed narrower in that region. But what it shows is that you need really advanced many-body perturbation theory to reconstruct the spectra. And if you do so, you really reach a nice agreement. But these calculations are extremely time-consuming, and they take hundreds of thousands of configurations. And we have also seen that using FAC of GU, we can reach a reasonable agreement with less effort, let's put it this way. But indeed, there are many other methods which can be applied. What we also have done quite a bit is resonant photoexcitation with ions trapped in the EBIT by injecting photons from synchrotrons and free electron lasers. And there we did some experiments with iron 16 plus, where we could measure directly, let's say, the oscillator strength by exciting from the ground state by using photons. And we measured their branching ratio, and that was a very beautiful experiment because we excite at 800 electron volts and we are doing laser spectroscopy. And it was a very nice thing, but we got probably a result which has to be changed because there were non-linear processes going on, changing population from iron 15 plus to iron 16 plus taking place simultaneously, and some non-linearities. So there is much more to come to this whole problem of the 3C/3D ratio, but I can advance that the latest measurements have shown that the theory, the most advanced theory is right. And that issues of non-linearities and resolution, which have been everywhere in astrophysics, in plasmas, and also in EBITs, have been until now the reason for this discrepancy. But this is still to be published. In the photoionization with EBITs, you take the monochromatic beam and you put it onto the EBIT, and then you extract ions and you look at them with your position-sensitive detector, basically experiments which have been shown elsewhere. And we were able to go quite far down, like nitrogen 3+, in our photoionization studies, and then also iron 14+, where you see very strong resonances, and the comparison with relativistic many-body perturbation theory at that time was already very, very favorable for relativistic many-body perturbation theory and Hewlett. And then we went up to even higher energies in the photoionization. What you see here is the excitation of iron 24+ with photons of 6.7 kilo electron volts at Petra. And what we see here is the fluorescence of the iron 24 plus in the resonance transition singlet P1 to singlet S0, but also in the intercombination transition triplet P1, triplet P0, which is narrower because it is less allowed than the other transition. And you can see it directly in the picture. And what we also did at the same time is extracting ions and determining their Auger widths. So we were exciting the ions on simultaneously observing fluorescence and the photoionization of iron 23 plus, iron 22 plus, and so on in the same energy scale. And very recently, we have started to do the same thing using miniature rivets. These things are, you know, the red part here, which you see, is a miniature rivet with permanent magnets, and it is like this big. And we use an off-axis electron gun on these machines for photon experiments. The off-axis beam brings the photons from the side and merges them with the photon beam. So the electrons come from below and they merge with the photon beam. So the photon beam can pass through the EBIT, and this has certain advantages, which I will show you later. So one of the reasons, one of the first applications where we are looking at the absorption of atomic oxygen in the interstellar space. And there was a long discrepancy. It looked like atomic oxygen was moving in the galaxies at 300 kilometers per second, and that was really not compatible with all other atomic elements seen around, and very close to the escape velocity. And atomic oxygen had been calibrated with molecular oxygen at the synchro with electron energy loss spectrometry many years ago. And we went to, so this is shown here, the absorption of the atomic oxygen, and this was crazy. The results could not be reconciled with what was expected. And Maurice Leutenegger traced it back to molecular oxygen calibrations done in the 70s. And this calibration was only done at that time, and everyone else has been using it unknowingly, because all the other people who presumably calibrated actually were based on this calibration. Anyway, we went to a synchrotron, we went to BESI with our EBIT, with off-axis electron gun, and we took the monochromator light, we took our detectors, and we put behind it a little gas cell from NASA. And in this little gas cell from NASA, which was brought by Maurice, we put oxygen molecules and a channeltron, and we separated both things, and then we scanned the photon energy. And so you send the photon beam, it goes to the EBIT, it goes to the tube, it goes to this gas cell. There you look at the photoions, and at the same time you are recording K alpha, K beta, K gamma of well-known highly charged ions. In this case, we use oxygen, nitrogen, and neon. And when you do that, these are our calibration lines obtained with the EBIT by looking at the fluorescence. And the black curve here shows the simultaneously acquired spectra of molecular oxygen photoionization. And you see here the shift between the calibration we have performed now directly and simultaneously, and the original values from Brion and Wright. And this is, by the way, yeah, 3 minutes. Okay, so this is great because we got the neutral oxygen to stop moving that fast in our galaxy, and now it is moving at the regular speed. So we did something for our galaxies. And we did also measurements recently at Petra with higher and higher resolution in the iron 3C 3D problem. You see here at 800 eV the fluorescence of iron 16 plus and iron 17 plus, excuse me, iron 15 plus and 16 plus, and we were able to resolve with very high resolution these transitions. And now we can address again the problem of 3C 3D without normalization and problems like that. And these are results from a few weeks ago. They are still unanalyzed, but we have obtained the photoionization of highly charged iron 13 plus. We have also the photo excitation at the same time, and we have reached much higher resolution than before, and we will have very beautiful results solving basically these discrepancies which were around. Here you can see beautiful Voigt profiles aligning this. Let me mention a little thing. EUV nanolithography uses highly charged ions of tin. You blast tin droplets with big lasers, and you collect the extreme ultraviolet radiation they emit. And this is a truly multi-billion-dollar industrial application. But we were able to investigate the optical emission lines from tin in collaboration with the Dutch group of Oscar Versolato, who at the time was in Heidelberg. And you want to have a posh PhD thesis defense, you want to have this subject. Yeah? What you see here is the EUV emission spectra, and these EUV emission spectra in the different charge states are obtained with the EBIT, and you can analyze it with theory. And basically, you go back to many body perturbation theory configuration interaction in order to be able to really predict the spectra. Of course, you can take K1 and fiddle around with parameters, but relativistic many body perturbation theory from Berengut can actually really tell you which ions are which and which lines are which. And these guys here are the ones which are making chips these days. And it is a very interesting effort involving EBIT spectra, involving theoretical analysis, and also involving later photo absorption in lesser produced plasmas. You see the the emission and absorption spectra of the plasmas here, and you can see how you have indeed Fraunhofer absorption in the range of interest, and that is analyzed with the help of the data from David. In summary, photorecombination and photoionization studies, they show more and more complex structures due to multiple excitations. We need very good theory to understand that, and also very good experimental resolution. And there are certainly very, very interesting applications for atomic physics, not only EUV nanolithography and astrophysics. And we need both aspects. We need good theory and good experiments for this. And so thank you very much for listening. And I would like to thank Sven and Chintan and Stephen and Peter and Stepan and all the students in my group, Oscar Versolato and so on, who have done a great job in this business. Thank you very much, and congratulations, Steve, on your birthday, or with delays somehow.
Thank you, Jose. Thanks very much. Thanks very much. Very nice talk. Are there any comments or questions? No. I might just ask something. Going right back to the free electron laser measurement on iron, you said that there was a population transfer through some nonlinear interaction.
Yep.
Can you expand on that?
Okay. So in the free electron laser case, actually there is a blend here between C, which is sodium-like, and 3D. And when you excite this with the bandwidth of the free electron laser, you have a certain population of sodium-like iron, and this population is really excited, but it has a decay channel, a decay resonance channel to iron-16+. So instantaneously, you are changing the population of 15+ to 16+ and enhancing the resolution. So this could only be solved if we resolve the two transitions, and that we did with certain tricks at the synchrotron later, and very recently with even higher resolution.
Okay, thanks, Jose. Thank you very much.
Excuse me, this is Yuri Ralchenko. I actually put my question into the chat, but probably it slipped some. So I have a very short question. Jose, can you please give us a hint what kind of advanced theory was able to get the 3C/3D ratio correct?
Okay, so if you look at our recent paper of Stephen Kuhn et al., all the theory there is basically correct. So we used Mariana Safronova's work, Julian Berengut did work, in our group, Salt and Harman did work. So everyone was involved, everyone was frying clusters and for weeks on without end and thousands of cores, and they converged around 3.55. And I must say that the last measurement we did a few weeks ago is going into that direction. And we are now really analyzing very, very subtle systematics effects which have pervaded in all earlier work, including our own work in synchrotrons. And it seems like the highest level relativistic many-body perturbation theory and CI, if you put 1 million configurations, you will get you the right result. And it looks like all the experiments before, including our own, had been, let's say, the uncertainties were miscalculated because there were very, very subtle contributions around that.
Okay, thank you.
Okay, thanks very much. Thanks, Yuri, for the question. So our next speaker is Lokesh Tribedi. Are you there? You're there, Lokesh. Yeah, I see you. And he's from Tata Institute of Fundamental Research in Mumbai. And his talk is on electron emission from iodouracil and the radio-sensitizing effect. Over to you, Lokesh.
Yeah, hello, yeah. Okay, I'm here. Let me try to share first. Just give me a minute.
Okay.
Somehow I first have to click this up, then share. Yes. It shows up something you can see.
Yeah, we can see it. We just need to go to full screen. Yeah.
Yes. Yeah. Yeah. All right. Yeah. Fine. Okay. Great. I think you can see. So.
Right. Yep.
Yeah, thank you so much. One big thing nowadays in the talk, as soon as your file is displayed, you are relaxed. Sometimes it doesn't display. Okay, so first of all, thank you, Professor Deshmukh and John, for inviting me for this nice conference and session in honor of Steve. So Steve mentioned, I wish you really many, many happy returns of the day. Nice birthday. Thank you. And it's a very nice occasion that we get together even in the pandemic situation. So my talk is basic atomic molecular sciences with highly charged ions and application, but this application part I'm talking. So basically my topic is same as you mentioned here. This is, don't worry about exactly this. This application is here. Basically, I'm going to talk about iodouracil, one of the molecules, and we look for electron emissions and so-called radio sensitization effect. So this is our institute, Tata Institute of Fundamental Research, and this is right in the sea, Arabian Sea. And this tall tower, what you are seeing, is an accelerator, one of our accelerators. And this is what you are seeing in the room. This is the accelerator, ECR-based low energy ion accelerator, which me and my group has developed last several years now. So we do experiments at high energy beam, so-called high energy beam, MeV energy beam here with highly charged ions, and keV to MeV energy range ion beams again with highly charged ions. I don't know why the screen is not moving. Okay, yeah, moving. So this I just remembered just to see, since we are gathering here in honor of Professor Manson. So Steve's very old, one of the very old paper, 1975, energy and angular distributions of electrons ejected from helium by fast protons and electrons. I remember many of our papers, I used to cite this paper. It is a very, very nice paper. And this paper, you see the page number 60 to 79. It's very, very nice to see a physical review paper of 19-page nice paper. It has a lot of information till now, a lot of citations of this paper. So thank you for this nice paper with Nico Stolterford and others. So this is our experimental setup in brief. This is, we have a hemispherical electrostatic analyzer, which we use inside the chamber to detect the low energy electron. Basically, we are interested in continuum electrons, not so high resolution. So one of the motivations, now a lot of measurements are aimed, as well as theory, are, for example, Monte Carlo simulations for proton track structure in biological matters. Okay, it's like Christophe Chapot from France, also Gustavo's group, they also did a lot of these calculations where they do really simulations. And this simulation needs a lot of absolute cross-sections of the data for biological matters. That means if ion passing through the biological matter, and for energy loss, for capture, fragmentation, excitation, and ionization at the Bragg peak energy. This is a lot of requirement for modeling the hadron therapy and radiation damage in hadron therapy. So, and this highly charged ion interactions with water molecules and DNA RNA bases, these are the inputs for hadron therapy required. Of course, it's much more complicated than simple measurement. And these are also required for the cancer therapy modeling and so on. So here is an example of energy loss in water. So this is like 200 multiplied by 12. That means something like 2.4 GeV. And this is like double of that, 4.8 GeV. You see inside that there is a Bragg peak. This peak is Bragg peak where maximum energy is lost at the end of the track. And at this point, the beam energy is actually much low. Although we started with GeV energy, here the energy has typically about MeV or less. So this is the energy range where a lot of things happens. And here we can show that this is the gamma ray, which not only give damage to the tumor, but also gives damage to other places. Whereas in heavy ion beam, it creates most of the damage in your tumor itself at the Bragg peak energy region. So our goal is to, in the Bragg peak energy region, can we measure certain cross sections? For example, the low energy electrons like 3 to 20 electron volt are known to most dangerous. So they cause the most of the damage. So we try to understand what is the probability of this low energy electron emission, their absolute cross sections and so on. So how to produce such more and more low energy electrons in the cells. So one such example I give you here, this is a total cross section measurements. Several years back, this is published by Aditya Almiotri, my student. This is the total cross sections of uracil ionization in ECR energy range, and this is at pelletron, that is high energy range. High energy range, the theory goes parallel, like red line CDWIS calculation, whereas lowest energy range, the deviation is very large, almost factor of 5. And this is our absolute cross sections, and this is very nice set of data over a wide energy range. Now the question is that in this energy range, is there anything better possible? So this is another theoretical model based on our data only. This is Montenegro's group from Brazil. They found out by a scaling mechanism, they found out a very good agreement with our data as well as their theoretical calculations. Only difference with previous CDWIS, that is continuum distorted iconal, continuum distorted over iconal initial state model, which is very fair and large successful model in ion atom collisions or ion molecule collisions. In this model of Montenegro, he added the ionization plus transfer, that is transfer ionization channel, which is true electron channel generally neglected. But at this low energy region, they play a major role. We could see a nice, good agreement. But further going, we had another example of adenine molecule, and adenine UPCDWEIS provides almost very excellent agreement. Although log scale, there will be small deviations here and there, but by and large, you can see the double differential cross sections at each angle, measurement angle, are very well reproduced by the line. So these are the continuum electron spectrum. X-axis I am plotting ejected electron energy, about 100 or 200 electron volt, down to from 1 electron volt. This is a very difficult region to measure at 1 electron volt region. But we are very happy to see very nice agreement in case of adenine. And it was published about a year back, 2019, in PhysReview. Now here I give another example of iodouracil. I am coming to that, but before that, there is a prediction by Solovyev's group. There is a PRL a few years back, 2015, that if you put a nanoparticle or a cluster of many particles like platinum or gold or and so on, or gadolinium inside the DNA, you enhance the low energy electron emission, and this low energy electron can cause further damage. The question is that how much energy enhancement, how much electron enhancement? That's the question we wanted to experimentally measure. And These are the metal atoms which can have a plasmon emissions, excitations, and this plasmon electron emission can cause the further damage and enhancement in the electron emission, which is useful to cause further damage or surrounding water molecules and so on to produce further low energy electrons. So we just took a iodine molecule, iodine, and if you add it with uracil is iodouracil. These are class of halouracils. So one of the iodouracil molecules, we did an experiment. Of course, these are the experimental techniques. I will not go to details. This oven, you have to create this biomolecule oven, and you have to do an experiments during this thing. And there is a lot of practical problems. You have a deposition, you lose a lot of low energy electrons. Sometimes you have to be extremely careful these measurements. In fact, heating itself takes 24 hours, properly suitable heating, very slow space, and so on. So here is the example of the iodouracil. One iodine is put in place of one of the hydrogen, and this is commercially available powders. So this is very similar to uracil, except one iodine, and it can be used. Whether can it be used as a radio sensitizer? Why should you choose iodine? You will very soon see that iodine is one like xenon. They have a giant resonance mode. So we wanted to exploit the giant resonance mode. And then we measured the double differential cross-section, that is the DDCS of electron emission using carbon ions, very fast carbon ions. Carbon means something like 66 MeV and so on. So this is very fast carbon ions. And here is the experimental setup. Of course, we do the deposition rate, measurements, and so on, just to make a uniform deposition rate. And base pressure is typically -7, -8 torr. These are just very standard technique. Only thing to say that we go about 120 degrees centigrade temperature. So these beams, of course, use different energy. Just one example is here. Now, uracil has 58 outer shell electrons. Okay, outer shell is 42 out of 58, and neglecting the K shell electrons. Similarly, iodouracil has, of course, larger number of electrons, 110 and so on. Outer shell electrons are 60 to 64. So ratio of outer shell electrons to inner shell can be 1.4 times more compared to uracil. But however, if you really combine with actually ionization probability, then you expect the ratio about 1.2 to 1.1. That means ratio between iodouracil to uracil. How much enhancement? So let us see what, that is the prediction of CDWEIS. Let us see what happens. Here is our experimental results. So here I plot different electron energies. Mostly we are concentrating in the low energy electron. For example, 20 electron in a electron volt energy here. You see, these are the blue, black points are the iodouracil data, where the red points are uracil data. You can clearly see the ratio is different from the prediction of CDWEIS. Yes, these two lines are CDW. One is uracil, one is iodouracil. They're much closer than the experimental data. Their difference is much more. And this is true for each electron energy. So now we want to see how the ratio is. So here I plot again experimental data for iodouracil to uracil, these two at different angles, And each case you can see there's a measurable, very good difference between iodouracil and uracil. And look at the ratio. The ratio comes, if you look into the numbers, between 2 and 3. Each energy, 21 electron volt, 40 electron volt, each case between 2 and 3. Whereas the theoretical prediction is the blue line, which is the CDWEIS prediction. It predicts about 1.1, roughly 1.1, 1.2 enhancement, each energy range. And we are concentrating mostly low energy electrons. So that is here. At each energy.
3 minutes, Lokesh.
Okay, at each angle, we have low energy electrons. So these are the, so at 2 to 2.5 times enhancements electron emission over uracil. But why? So theory gives 1.10. So rest we conjecture that due to the giant resonances. So here is the theoretical prediction from CDWEIS. Let me get out from this. So iodine is known to exhibit atomic giant resonances like 4d2 epsilon F excitation, and this has a typically peak energy as a 90 electron volt, and this state decays by low energy electron enhancement. Due to the 4d electrons, we see this enhancement of GDR. And that energy is 90 electron volt, width is a very 40 electron volt. This part is known from the literature. So that is one reason which gives this kind of enhancement. I show the enhancement again here. So more than 2 times enhancement in uracil in agreement with the prediction Now this GDR prediction was done in Solovyev's paper, which is for, of course, silver, but we tried to do from the same paper, and when you put the numbers properly, suitably, we could get this enhancement. And interestingly, this paper is just now published, 2020, and December 14. Why I am putting the date here, that this is the first day of the AAMOS conference. That it was very good that this paper was published, and we try to show this enhancement. Now, just before I go out of this, I just wanted to show one result on our C60 measurements. Similarly, we could see the C60, you look into the angular distributions by fluorine ion, 76 MeV. The angular distribution typically shows a peak in ion-atom collision at each case, but except one case. These are lowest energy electrons around 7 electron volt or 8 electron volt, where we expect a giant resonance in case of C60. And I plotted here, these are giant resonance. Due to that, I can see the angular distribution, so it's a very nice dip. We agreed with the photoionization kind of model with the polarization along the giant dipole resonance, and C60 emits the electron, and this photoelectron emission formula, when we put, of course, we have to correct for post-collision interaction and so on. These are also published this year. We could see nice agreement in this GDR, another case like C60 case. So now this radio-sensitizing effect or electron enhancement, we could found 2.3 or 2.5 over water. And that was the prediction also on the CDWIS, on the giant dipole resonance model, whereas CDWIS did not work because it does not accept the large electron correlation and giant dipole resonance effect in the model. But one interesting thing is there was only one measurement in the literature in which they had really done the measurements of radio-sensitizing factor for platinum and gold nanoparticle in the DNA strand breaking study. And this was a Purcell in 2010 in nanotechnology. They had also seen a similar enhancement, like 1.8 or factor of 2. So that was a very good thing for us to see. So this is one of our papers have been recently accepted as a highlight or news in EPJ. I'm happy to share this on paper on adenine, and some of these are in the review article recently. I have recently published already. One of the Singapore World Scientific Singapore by Belkis, and this is the book in which there's a roadmap, and also there's a EPIC roadmap article which was published. Many of you are here, perhaps co-authors. One can see some of the details there, and some more review are supposed to come. So this is the, I think I'll skip this. So this is my students and postdocs and theoretical support. So this particular work on iodouracil by Anubhav Mandal and several students have contributed. We have a very good theory support from Rivato Rivarola, Chapo, Juan Monti, Gulias, and Phil Weck. And I thank all of them. And thank you very much. This is TIFRC side.
Thank you, Lokesh. Thank you very much. So do we have any questions or comments on the talk? No, none in the chat. So is it clear? So you talk about low energy electrons and the importance of low energy electrons. Is it clear why they're so important in this DNA damage? Is the mechanism well known at this stage?
Yeah, I think this is mostly known as their DEA, dissociative electron attachment. So these lowest energy electrons, actually it is so low that sometimes even below ionization threshold, they cause damage because they got, they get attached, create a transient negative molecular ions, and then they finally get dissociated. So this is very well known as dissociative electron attachment. That was the prediction of Leo Schanz's group, and now I think is well known, this mechanism.
Okay. Any other questions, comments? A minute or two. Okay, if not, thank you, Lokesh. So we've had a number of experimental talks. Last time I talked to Patrick, he was a theorist.
Thank you so much.
Yeah.
So Patrick Palmeri from University of Mons in Belgium, and Patrick's talk is on multi-configuration Dirac-Hartree-Fock radiative parameters for emission lines in cerium ions and cerium opacity calculations for kilonovae. Over to you, Patrick.
Yeah, thank you, John. And I thank the organizers of the meeting for welcoming me to give this talk, actually. And
are you able to share your slides?
Yes, I will share my slides. So So can you see my slide?
Yes.
Okay. So actually, I will present the work of the master thesis of our student. It is a master thesis of Hélène Carvajal-Gallego under my supervision and Pascal Quiné's supervision.
Can you speak a little louder?
Yes. Yeah. Can you hear me now?
Yes, now it's better.
Now it's better. Okay. So I will first introduce the motivation of that work, and then talk about the atomic net data calculations. This will be the first part of my talk, and then the opacity calculations, and then I will draw some conclusions. So the motivation is the first detection of a kilonova, and a kilonova, it's produced by a neutron star mergers, and the first detection was done 3 years ago in August 70s by a collaborations of the LIGO and Virgo experiments, who detected gravitational waves, and a few days later, telescopes detect the afterglow of these mergers. So actually, when two neutron stars spiral and orbit together, they generate gravitational waves, lose energy, and the orbits spiral down and finish by merge. And this creates an explosion. Matter are ejected, so you have an ejecta, and the ejecta is rich in neutron, and neutrons, and then these neutrons from the neutron stars actually react with the elements and produce nucleosynthesis with rapid neutron captures, and the heavy elements, radioactive heavy elements, decay, radiative decay, and power the kilonova. And you have this glow of so-called quasi black body radiations from the kilonova with absorbing features. And this afterglows spectra were recorded a few days later after the merging, and they show spectra from the optical to the infrared for most of the parts. And the group of Cassons show that these afterglow, actually the red part of it, are affected strongly by the opacity of bound lanthanides. And the contribution of these lanthanides is an order of magnitude with respect of the contribution of the iron group elements formed in the neutron star by the neutron star mergers. And they conclude that this arc process, this event of neutron star mergers is by far the most effective site of producing arc process elements in the universe. So as you see here in the infrared bands, in black curve you have the observations at 5 days after 4.5 days after the mergers, after having detected the gravitational waves. And you have this modeling, which is based on a multitude of lanthanide lines absorbing this black body radiation powered by the radioactive decay of this EV element. And you have here this is a mass fraction of lanthanides, this is 10 to the minus 2. And you have an ejecta of 4% of the solar mass. And this shadow area is just to tell that you are observing from Earth, and you have also contribution for telluric lines. So you have to correct this contribution from the spectrum. So the most important thing to know is this bound opacity dominates coming from the lanthanides due to these many lines, high density lines, due to the open F shell, 4F shell in the case of lanthanides structures. But Carstens, when they model this opacity, use actually a very rough estimate of these lines. They use basically auto structures with really crude estimates of the line positions and oscillator strengths. So there was a real need, a call to a more accurate opacity, bound opacity due to lanthanide ions. In Mons, we have a database called a DREAM database. They contain a lot of lines, many lines, 70,000 lanthanide lines from second to fourth spectra. These data are semi-empirical and use Hartree-Fock structure program to produce this data. So it's oscillator strengths and wavelengths. And it was mainly designed to help to determine stellar abundance of these elements. But this is not enough. After this, to respond to these needs, Lithuanian and Japanese teams come together and start to produce systematic large-scale calculation in order to obtain this atomic data for the second to the fourth spectra of the lanthanides. So basically, they did neodymium, europium, doing MCDHF calculation, and praseodymium to gadolinium-2 for this highly accurate large-scale MCDF calculations. And they did the rest with the ULAC codes. And they estimate also opacities. But there was still a need of the contribution of this opacity, the conclusion of Carsten group. They searched for the main contribution, and then they saw that neodymium and cerium were of the most contributors to these opacities. So there are still lack of cerium atomic data. I mean, for large scales data to be compared with this observation. So we did large scale MCDHF calculation in the cerium ions 2 to 4. So this is a basic, this is a main ionization stage that contribute to the infrared part of this kilonovae, because the temperatures is of the order of several thousand Kelvin and to 10,000 kelvins. So you produce all these charge states are expected to contribute, and we did these opacity calculations. So what are these lanthanides? The lanthanides, if I take the periodic table from the list, for instance, this are the element from Z equals 57 to Z equal 71. And cerium is the element of Z equal 58. In cerium, you have this big xenon core with 4 valence electrons, with this characteristic F electrons of this group, 4F electrons. So we did multi-configuration Dirac-Fock calculations. So these methods, we use the GRASP 2018 atomic structure package of Fischer et al. In this model, the atomic state function psi is modeled by a superposition, an expansion of configuration state functions in JJ coupling, which are JJ coupled function of spin orbitals, monoelectronic orbitals, and actually these in the multi-configuration Dirac-Fock theory, we optimized this radial part of the spin orbitals and the coefficient of the expansions in a self-consistent field procedure by solving the radial equations that minimize a certain energy functionals. Here we will minimize the energies of the our spectroscopic energy levels we want to study.
Patrick, you have 3 minutes.
Oh, okay.
Right.
Too long. So, well, so we include Breit and QED effects, and these are the strategy of optimizations. So we use this multi-reference. These are our spectroscopic configurations we want to reproduce in order to produce these opacities. And we include valence-valence correlation in a systematic way, adding layers of layers, layer by layers. And we also include covalence interactions. You see different models of covalent interaction involving core electrons from the xenon core and promoting single double excitation to the shell of, basically the shell of the multi-reference configurations. And these are the size of each of the matrix as a number of CSFs of the expansion, and you see it grows really fastly. And when you include core-core correlation, you see a big increase of the size of the matrix. So it should be limited. And we monitor the convergence of our calculations with wavelengths, with respect of wavelengths. This is the different step of the calculations. This is an example for 2 lines in cerium 2. And we monitor also the transition, the conversion of the transition probabilities and the agreement between the Coulomb and Babushkin gauges. We monitor also the energy levels, and we compare with NIST, and this is only valence calculations. This is the example of cerium-3. And you see when you include core valence, quickly the distribution of the deviation with respect to NIST diminished, and the distribution becomes more symmetric. And then when I include more core valence correlation, you see that you have really a good general statistical agreement with the NIST energy levels, the experimental ones. So you need to include core valence. We compare it with the DREAM transition rates, so basically the semi-empirical rates from DREAM database. We have an overall agreement for all the ions of around 30%. This will show you for an example for the most intense line in cerium-2 from DREAM and GRASP. And we also checked we compare with measure lifetimes. Here in cerium-4, there was no lines in the DREAM database, and we see that this lifetime for the 5D doublet is of an agreement of 20%. So we made some calculation, opacity calculation, and we use the expansion opacity formalism, originally introduced by Karp et al., and where the bound monochromatic opacity depends on the time after the merger, and the Sobolev optical depth, which depend also on the times, and the oscillator strength, of course. And the population of the lowest levels, which is the number density of the lowest level of the transition, is estimate in a local thermodynamic equilibrium model.
Patrick, you're down to about a minute.
Okay.
Never.
So we did it. This is a number of lines. So we include a lot of lines. This is our work. This is three times or even several times the available number of lines. This is important for the opacity. You want to be complete. And this is the comparison with DREAM. You see that we have a greater opacity due to the lack of lines in the DREAM database. And this is the resolution of the bin sides, the resolution of the monochromatic opacity. We did this for different expansion elapsed time after the major is up to 1.5 days. You see the very nice dilution effect due to the expansion of the materials, and so the opacity drops with the time t. So my conclusion, this is a new large-scale MCDF calculation for the cerium ions that include valence and covalence correlation in a systematic way, and we have a good agreement with the NIST experimental energy levels by a few percent for most of the levels, and we did have a good agreement with the semi-empirical transition rates of the DREAM database, about 30%. We include an extended set of lines. This is important to get a complete for the completeness for the opacities. And we see that our MCDF opacity is larger than those computed with the DREAM data sets. This is due to completeness issue. And this result has been accepted for publication in the monthly notices review. And the future work will be done for highly charged lanthanides. Basically, the 5 to 10 spectra of the lanthanides. So I thank you for your attention.
Okay, thank you, Patrick. We're down to about 45 seconds. If there's a quick comment, we'll take it. Otherwise, if somebody wants to put their questions into the chat, which is what we, and I noticed it's been active with people working on it. Okay, if there's no comments, then thank you, Patrick, and we move on to our next speaker. Next speaker is.
Thank you.
Hello, Yuri Ralchenko. Yuri, are you there?
Yes, I am.
Oh, great. Okay, excellent. Are you able to share your screen?
Well, I hope you can see it.
Great. So Yuri Ralchenko from the National Institute for Standards and Technology in Gaithersburg, and the title of Yuri's talk is Testing Quantum Electrodynamics with Defined Structure Splitting in Highly Charged Fluorine-like Ions. Over to you, Yuri.
Thank you, John. And first of all, of course, I would like to thank the organizers and John in particular for this invitation. I've never done any work with Steve, although we were certainly meeting at different conferences, but his many papers on photonization were always benchmarks for us guys who use tons of data in plasma diagnostics, and which definitely need this important benchmark to better see what we do and how we do it. But what I'm going to talk about today is not about plasma diagnostic, but rather more fundamental things relating to testing QED techniques with kind of simple systems, in particular the highly charged fluorine-like ions. First of all, let me, let me acknowledge my dear colleagues who contributed greatly to this work that has been published in PhysRef a few months ago. A group from NIST, both Gaithersburg and Boulder, and also Clemson University, Harvard, University of Colorado, and in particular Andrew Volotka, who provided excellent calculation for this work. And the story actually starts 2 years ago, and I'm very glad that Roger Hutton is here because he was one of the authors in this paper that pointed out a nice way to test Breit and QED effects in the ground state of 2p5 configuration of the fluorine-like isoelectronic sequence. Obviously, when we look at F-like ion, we immediately see that the laser complex, which has configurations of the same parity and the same distribution of electron along in shells, has only one configuration of negative parity, 2s squared 2p5. You take 2s to 2p and it becomes a different parity, or you take n equal 2 electron to n equal 3, it goes far away, and therefore it turns out that correlations are strongly suppressed for this configuration. The authors of this paper called it laser quenching, and basically they pointed out that because of this suppression of correlation within 2s squared 2p5 ground configuration, we can look at the M1 photon, measure the transition energy as accurately as we can, and try to understand what contribution of relativistic and QED to this transition is. So in this paper, they use GRASP2K codes to do calculation, starting with non-QED MCDF type wave function, then adding frequency-dependent Breit configuration, self-energy contribution, vacuum polarization, and compare the results with experiments and other theory. And as probably everyone would have expected, at very low Z at lightest elements, where QED Breit are really very weak, everything agrees very nicely with GRASP. You go to higher these, and you immediately see some disagreement. Now, also, this paper has comparison with additional contribution, one from Walton, very well-known Walton model that basically agrees well with Crespo, but also they included model QED calculation based on the model developed by Vladimir Shabayev and his colleagues. And as you see here, the blue triangles kind of disagree a bit at low Z, although at higher Z, they seem to fall within the error bars. Then next year, Andrei Volotka and his colleagues and Yan and GSI and other institutions performed ab initio QD calculations that were non-perturbative in alpha Z expansion parameter, included all first order and many electron second order effects in alpha. They got these new results that are shown in red. The other points you've seen on the previous slide, but you immediately notice that the red dots agree with the experiment, which is in black here, practically everywhere. Importantly, theorists provided uncertainties for their calculation, and that was really nice. But you see the uncertainties are quite large for low Z, for low Z elements, but then, of course, shrink at higher Z. So for tungsten, the theoretical uncertainty was very small, but experimental uncertainties were really large. So the question that we asked was, can we precisely measure and with help of theorists accurately calculate the M1 transition in other highly charged fluorine-like ions in order to continue testing these QED effects? And the tool, experimental tool of choice for us, of course, was the electron beam ion trap, and I'm very grateful to Nakamura-san, Roger, and Jose for explaining everything about IBIS that I would have needed in this talk. So we're going to look at krypton, which is a gas and it can be injected. Krypton has been measured already, so we were hoping to improve the uncertainties. And then in our IBIT, we have so-called metal vapor vacuum arc, a set of electrodes that allows us very easily to switch between different metals to inject atoms of, say in this case, tungsten, rhenium, osmium, and iridium. Tungsten has also been measured, but rhenium, osmium, and iridium would be new elements in this story. The energy that we needed to produce fluorine-like ions are all under 20 keV, which is good because our IBIT, unlike other super IBITs, can go up only to approximately 30 keV, so we're well in the range. And of course, because krypton has wavelengths for this M1 transition, EUV, and heavy elements are in X-ray, we had to use two instruments, EUV spectrometer and transition edge sensor microcalorimeter. So EUV measurements were done, as I said, with this ultra-high vacuum flat field EUV spectrometer that covers spectral range between 1.5 to 26 nanometer. The resolution is not very high. However, it is sufficient to not only see, but quite accurately measure the wavelengths or energy of this transition. So what you see here is the measured spectra from two EBIT energies, 3 and 3.5 keV. At 3, there is nothing here. At 3.5, we clearly see the line. And of course, since ionization potential of the previous neon-like ion is under 3 keV, this is what we would have expected. So we took measurements at 5 energies for krypton, nothing at 2.5, nothing at 3, and of course we saw this line. The total collection time to get very good statistics for this M1 transition was total of only 2 hours, 20 minutes. So this is about EUV krypton. For heavy elements, we use the brand new transition edge sensor X-ray detector or microcalorimeter, which basically is a thermometer. So photon comes on a specifically selected material. heats it up a little bit, and since the material is held at sub 100 millikelvin temperatures, actually it sits near the superconductivity transition edge. So it heats up a little bit. Its resistance changes rapidly and significantly. So from this change, we are able to determine the energy of the photon that hit the chip. The microcalorimeter, which we call NATS, was set up just 2 years ago, a bit before all coronavirus thing kicked in. The first spectrum was obtained literally almost 2 years ago. And basically we have not one, but 192 spectrometers sitting on the top of this small chip that is held at temperature of 70 millikelvin. Huge advantages that it covers very large range of between 500 to 15,000 electron volts and provides excellent resolution for electron volts at 6 keV. This example of the very first spectra that we got 2 years ago, you see very nicely resolved isolated line from osmium 47 plus, approximately nickel-like ion, and our theoretical modeling, you see, could explain practically each and every feature that we saw in the spectrum. And of course, we were very happy with the operation of the microcalorimeter. This example of this M1 transition that we measured for rhenium in this experiment, collection time was only several hours, again, very good. We had good calibration with K-alpha lines of light metals and cases, because the energy is about 1500 electron volts. And our experimentalists spent so much time figuring out main contribution to systematic uncertainties like gain drift, calibration issues, and so on and so forth. So this is the primary result in the table. This is the transition energy from our work. These are previous measurements, and this is a result from Andrei Volodka's calculation. Again, it's Abanishuk QD calculation, perturbation theory, everything included in the first order, many electron second order effects are included. So what we see here is, I'll show you a plot at the next slide, but what is certainly seen here is that we significantly improved the precision of the measurement. Of course, this is the last digit value for the uncertainty, and we are going basically after the next digit. So is improvement a few times here. Improvement is probably a factor of 3, and there's a brand new data for this elements: rhenium, osmium, and iridium. Table is good, but let's take a look at the plot. So again, the black dots are our result from this experiment. You see in blue the previous experiments that done for krypton and tungsten. I'm showing here only the data that we measured. You saw the first slide that actually many more experimental points were taken for lighter elements in particular, but let me concentrate on this. So significant improvement in precision of the measured data, both for krypton and tungsten. Volodka's results, as you see, agree, which are in red, agree with the experiment everywhere very nicely. Here's where overlapping in the error bars, but still it's there.
3 minutes, Yuri.
Yes, thank you. I'm going. Then the original grasp 2K calculations from Roger and his colleagues did are shown in green. They're, as you see, somewhat outside the data for krypton and for tungsten, but this was not really unexpected. But certainly this point from Shabayev, the new work that actually was inspired by Roger's group's work, still sits outside error bars for krypton, although it agrees nicely with our latest data for tungsten. But here, as you see, it's like many sigma difference for their new model QED method. They took their old method and added some improvements. They agree for uranium data point, but here there's quite some disagreement. But it was very nice to see that this ab initio Volodka's method agrees very well for all elements that we measured here. So coming to conclusions, it seems that our EUV and X-ray measurements of this M1 transition energy within the ground state configuration of fluoride-like ions provides very good tests of QED contributions. We agree very well with ab initio QED calculations by Volodka. We would certainly love to see Vladimir Shabayev and his colleagues adding new data points for the elements that we just measured, and certainly we would love to see their theoretical uncertainties. Andrei did quite some effort to realistically estimate what his uncertainty are, and we encourage all theorists to follow in this direction. And we plan to extend the measurements to even heavier elements, for instance, gold and platinum. We do have electrodes that we can add to this MIVA metal vapor vacuum arc device on our EBIT, but well, we'll see. Still NIST is operating only at 20%. Most of us are not allowed to come to work, and this certainly hits our experimentalists very, very hard. And the last note, when I saw the program and Patrick just gave talk about lanthanide opacity, I just would like to announce that brand new NIST Los Alamos lanthanide opacity database will be released very soon. Actually, we're just polishing it a little bit. We're hoping to release it just before the New Year's, but if not, definitely by mid of January, we'll have this new database. Let me finish here, and happy birthday, Steve.
Thank you, Yuri. Thank you very much. Do we have any comments or questions on the talk? Any observations? Oh, I guess you're in contact with Vladimir Shabayev anyway to tell him that there's 3 more data points he should be calculating.
Yeah, no doubt.
Yeah. So, any other comments or questions? If people have a comment or a question, they can certainly put them in the chat as we go along, and then I'll come back on those. Oh, okay. So look, thank you very much, Yuri. We're Tu-Nan Chang, are you there? Yes. So hold on a sec. Sorry, I'm just going to have to check participants.
Yeah, unmute yourself, Tu-Nan.
Yeah, I see you.
Yeah, I'm trying to find all of a sudden that the unmute button disappeared.
Oh.
Did you see the? Let me see.
So, are you trying to share your screen?
Yes. Let me try. Okay.
So you should be able to just press on share screen and then click continue.
Yes. Let me do this.
Steve Manson and I have known each other for over 45 years. It started when Steve...
So we can hear, but we can't see because...
You cannot see anything?
Switch to tabs. Switch the window.
Let me see.
You have to share the window with the video that's playing.
Yeah, that's what I thought I did. I actually tried. Let me see.
So when it plays in a different window.
Okay.
You're on your desk.
Did you see it?
Steve Manson and I have known each other for over 45.
No, not yet. Maybe you can also share the full screen.
Minimize, sir, minimize that window, sir.
Well, actually, you know, on my own computer, I can see it.
Okay.
Yeah, so
maybe was it Ravi or somebody said that? Maybe you see the minimum when you play it, minimize your window.
When I played it, I minimize my window.
I guess maybe a particular window is shared. Maybe if you share the full screen, that might help.
Yeah, you can share the full screen.
Let me see what
go back to the share screen, the green arrow there.
Yeah, maybe you can unshare now. Then when you share again, we can.
Right now, could you see me right now?
Yes, we can see you now.
You can see. So right now, my screen shows everybody.
Yeah.
Listen, select share option, so share screen.
Yes, then share screen. And could you see on your anything on your screen?
Not yet, sir. Yeah, we can see, you know, something.
It's coming.
So it's sharing your directory, so you have an MP4 file.
Manson and I.
When you play that file, then minimize the window.
I'm glad that both.
You don't see anything right now.
Yes, we do.
Steve Manson and.
Okay, could you see it?
We can see. We can see. Are you looking at?
I'm looking at the first view graph.
No, what we're seeing is the directory with the 4 audio files and the MP4 video file. But we don't see the when you click on the video file to make it play, we don't see it. We continue
and I have known each other for over 45 years.
So you can close this window.
If you close
that. In that case, why don't I try to just give a talk instead of giving you the video? Okay, let me go back and you know, try to get to my talk. Could you see anything? Could you see my view graph?
Doing something weird.
Do you see any my windows?
No, we see the files, the thumbnails of the files, but we don't see the. Has it opened on your screen?
Yeah, it's open on my screen, but I don't seem to.
Okay, so when you open it, click on the little icon that gives the full screen, and then we might see it.
Let me see.
So open it first, then try to share the screen with the slide.
No, I opened that.
There you go. Yeah.
Did you see anything?
Yeah, now we see it.
You can see it.
So if you just click on to make it full screen.
Okay. But my background is already showing the full screen. But let me do this.
Click on that. Yeah.
Did you see that?
Perfect.
All go.
Okay, so everything you see that. Okay, so I'm sorry for the time wasted. Okay, so yeah, Steve and I, of course, we have known each other for over 45 years. Okay, it started when Steve had the whole head of hairs. And so you can see that in Ravi Rao's picture of 1974 that we took at the DEAP meeting in Chicago. So I'm glad that Steve and I, we are still working and we actually enjoy what we are doing. Okay. Now, what I am going to present to you today is a program actually I started about a few years ago. As a matter of fact, it's after my retirement, which is an application of known as the Debye-Herschel approximation, which was developed 95 years ago, which is actually before the quantum mechanics. And it is based on the classical Maxwell-Boltzmann statistics for atomic process, subject to the outside plasma environment. So my co-workers are listed on this particular view graph. Now, since atomic physics, atomic process are quantum mechanical phenomena, and for those interesting atomic transition subject to outside plasma, especially in the dense plasma with the density that is close to solid. Nobody in the plasma physics or actually in atomic physics believe that the Debye-Herschel model should be applicable. Okay. Now, so now let's just take a look at how the physics situation is. Okay. So you can see the center, the four centers, which is the nucleus, and it's surrounded by the outside plasma environment. Okay. And as early as in 1920, at that time, we already know the Rutherford atomic model is already well known. So everybody accept this model, except the question is whether this is going to work. Okay. So the next one shows that we actually apply the old Maxwell equation, the Gauss theory, which is given by this equation, where rho is just the density at the large distance r. At infinity, rho equal to rho 0, and the potential is equal to 0. Okay. Now, there are positive and the negative charge inside the plasma. So what happened is that once you have that charge density, you can write down this expression. Now, it turns out that when the temperature or the kinetic energy of the electron is substantially larger than the potential energy, then this whole equation can be linearized and is known as the linear Poisson-Boltzmann equation in taking this form. And here there's a one parameter, which is called the Debye radius, which is the ratio of the temperature and the density. Now we can change this expression to the following in a much easier way to be applied. Now, in this case, the temperature is given in electron volt, and the density is given in the 10 to the 22 cubic centimeter per cubic centimeter. In our study, we have introduced a new parameter, additional parameter, which is we call the reduced Debye length, which is nothing but the effective nuclear charge multiplied by the Debye length. For the helium-like ion, which is the one I'm going to talk about today, that Z effective is nothing but Z minus 1. So now let's look at the potential. Okay. Now inside the Debye sphere, this is trivial, of course. And outside the Debye sphere, we had the equation earlier. So by solving those two differential equations, which is relatively easy, and matching the outside potential and inside potential and outside potential, and their first order derivative at r equal to a, we will end up with a potential which looks like this form. And this is the form inside the Debye sphere and outside Debye sphere. Now, if we assume a equal to 0, okay, let the Debye sphere goes to 0, then this potential end up with the so-called screen Coulomb potential, which is actually in the same form like Yukawa potential in nuclear physics. Now, in order for this approximation to be working for the atomic process, there are two important criteria. And the reason that early days people say this won't work is because we really didn't bother these two important criteria. The first one is a temporal criteria. Okay? That is to say the lifetime of the emission is order of magnitude from the characteristic time of the outside plasma. Okay? And either much longer or much shorter. The other one is the spatial criteria. That is the outside plasma only marginally affect the atomic orbit. In other words, atomic orbit still have its quantum mechanical characteristic. So if those two criteria tells us that the level of the transition we're talking about, n cannot be too large, it has to be small. So in our case, we have chosen n less than 3 make equal to 3 or less. And the nuclear charge, if you look at the lifetime of the transition, it turns out the nuclear charge will be something between 10 and 18. Okay? So in our calculation, we have select the radius of the device sphere equal to the a constant, a parameter eta, multiplied by the radius of the electron in the ground state, okay, which is we call the RG. With that in mind, then we find that we can start talking about physics. Okay. Now, it turns out that all the transition is undergoing a redshift. And this is, of course, limited to the intra-shell, that is changing the principal quantum number. Then we have the redshift. The reason for redshift is relatively simple because the plasma field is less negative than the attractive nuclear potential. So in other words, there's an uplifting of the energy level of the atomic orbital. And this uplifting is bigger for the final state, which is inside state, and because the energy is greater. And the uplift for the upper state is actually smaller. And the end result is the reduction in the photon coming out from the emission. So in other words, the redshift for the intra-shell transition is necessary. Okay, that's just a simple consequence. And in terms of the theoretical calculation we have carried out, because this is, although it's a 2-electron system, but it's a very strong configuration interaction. So we have done the non-relativistic as well as relativistic calculation. Okay. Both calculations are multi-configuration, and in particular in the non-relativistic calculation, all the continuum orbital were included in the calculation. Okay. So this is the result that I'm going to talk about today. The first one is the result for the helium alpha line, okay, helium alpha line, that is from 2p to 1s transition. And here there are 3 different ions being included. And I should note that both our non-relativistic and relativistic calculation will lead to a plasma-free excitation energy, which is in agreement with the NICE data, which is agreement is less than 0.1%. So so we have the numbers. So what? Big deal, because the important question now is whether this is applicable to other systems and what is the physics behind it. And it turns out that if we look at the ratio of the redshift versus the plasma-free energy, we find that all those 3 ions, okay, it turns out this ratio actually follows a single curve. And this curve actually could be fitted with a simple polynomial. It's a constant plus another constant divided by lambda, which is the reduced Debye length, and another constant divided by lambda squared. Okay, so this is fairly universal feature. And it turns out for the other example, which I will talk about, for the helium beta decay, we'll also find that this universal curve is there. So the question is why? Now, turns out that if we follow the quasi-hydrogenic approximation, okay, then the redshift of the emitted photon is simply equals to the difference between the potential, the expectation value of the potential, difference in potential from the initial and the final state. Okay, qualitatively, that's what it is. So that is given by this. Now, take, for example, if we start with the simplest one, that's a 2p to 1s, okay, for the helium alpha line. And by just putting in the freshman physics, the upper division quantum mechanics, hydrogen wave function, and it turns out, indeed, the ratio comes out to be given by this expression, which is function of the reduced Debye length. And of course, more conveniently, this can be fitted into a simple expression, which is constant plus b over lambda plus c over lambda squared. Okay, and that is what we find out. So in other words, the model we have actually works to get to this far. Okay, now if we go back to what's the practical application from that? If we go back to the definition for the Debye length, now for a combination of kinetic energy as well as the electron the plasma density, from that, of course, is connected to the lambda. And because we already know the relationship between lambda and R, and by knowing the plasma free energy, then we'll be able to get the finally the redshift. So in other words, one can get this redshift for any ion which satisfy the criteria I talked about earlier. So here we have one of the results. Okay, this is the helium alpha line for argon ion, and it turns out that in 2017 there's an experimental result coming out. Okay, that the experimental result is, of course, that's taken between the temperature 250 to 375 electron volt. Of course, there are a lot of uncertainty because it's hard to decide. So those are the three curves we calculate, okay? And the experimental result is given by the black dot here. So you can see that actually the agreement is fairly well. Incidentally, I have to point out, and those two papers were published in the same year, and actually we do not know each other's work at all. So this is really not just a coincidence, or that we actually talked about earlier. Okay. Now, the next example, as I said earlier, this is the beta, helium beta line. Okay, so 3p to 1s calculation. Again, we find that this ratio follows a universal curve. Okay, follow a universal curve, fit in a very simple polynomial. And once we get this, then of course, just like earlier, we will be able to get the the redshift. And this is the comparison between theory and experiment. The experiment was done last year, 2019, published last year, with a kinetic energy between 600 and 650 electron volt. So you can see again, our estimated redshift is a very good agreement. And by the way, those numbers we have here were published were calculated even before the experiment. But of course, we didn't know the people were doing the experiment. So it turns out this agreement is pretty good, except here you notice that those are done at a different Debye, the radius of Debye sphere, okay? So there's an uncertainty in theory that is that much. Of course, this uncertainty is still smaller than the experimental uncertainty. Now, the implication of this particular figure is that we do have a way to estimate the redshift theoretically, but we still don't know exactly what is the eta value which can be used. And by the way, because this applies to all the ions, okay, all the ions. So my conclusion today is, since more precise estimate of the redshift depends on the size of the Debye sphere, so more experimental measurement that could offer a better determination of the radius of the Debye sphere. And together between the theory and our simple approach and experiment, that ultimately might lead to a better diagnostic possibility for the dense plasma. So that should conclude my discussion today. And finally, thank you for the organizer. Of course, happy birthday for Steve Manson. Okay, thank you. Bye.
Thank you, Tu-Nan. Thank you very much. Do we have any comments or questions on the talk?
Oh, very good. So everybody's convinced.
Yeah. So now it's time to go and measure.
Yes.
Okay, if any questions are coming up, I'm looking at the time here. So if any questions are coming up, please put them in the chat. And then what we'll do is we'll gather them up from the chat and we'll ask people to respond to them in due course. Thank you, Tu-Nan. We are now at the end of this marathon session. We have one more talk. So our last speaker, Horst Schmidt-Wilking, comes from the Goethe University in Frankfurt. He's going to give a sort of mixed historical talk and up to date. The title of the talk is High Resolution Momentum Measurements, Its Milestone Contributions to Quantum Physics. Horst, you're welcome, and you have the floor or the screen.
I hope. Okay, I pushed on share screen. Is it there?
No, not yet. So first launch the presentation.
What I have to do, I push on share screen.
Yeah, but do you, if you push on share screen, do you see? Sorry, hold on.
Okay, now it's there, huh?
It's coming. Yeah, it's there.
There you go.
Okay, I hope I'm there. Okay, Steve, even if I gratulated you on your birthday, I do it here again. I give you the warmest congratulations and best wishes for health and active and lucky life, particularly in physics. And from the whole group in Frankfurt, Reinhard Dörner will do it probably again, but okay, we can do it several times. This picture was taken in Atlanta in 2010 when you organized Lou's 70th birthday in Atlanta. Rose. And I made my first contact with you in 1975 on the ICPIC Seattle meeting. And then we have met on many occasions on conferences like here. This is a picture I found in my photo collection. In Leipzig, you see the two guys, Steve here and me. And a little later on the next meeting in Debrecen in the same year. And then many, many other follows, but unfortunately I found no pictures of that. Okay, you were, for me, I already told it you, a very, very special theorist, because very seldom an experimenter finds a theorist who speaks or can understand the language of experimenters when they have crazy questions. Normally theorists teach you then why you are wrong, but you went with us in the dark forest and tried to dig a hole and help us to follow and to proceed with these ideas. And often these ideas were not so stupid, and finally they gave good, very good results. And one of the famous examples is this man, Otto Stern. It's about exactly 100 or 101 years ago when he invented the molecular beam method. He started this in Frankfurt in 1919. And he, as experimenter, he has always a chance to explore new things because he has only to find out, but that's the most difficult thing, the error bars. But then he knows within the error bars there is a truth. On the other side, theorists, they have to make any model of the world, of nature, and in principle they are blind. But okay, the theoretical model only can then be valid if it's proven by experimentalists. And that's important. And one of these methods, which is very successful to bring new results, was is the momentum measurement. And this was developed by Otto Stern because he was the first which used particle in vacuum and got an excellent, as I will show later, an excellent resolution. He measured with a simple method with practically a straight camera in Frankfurt in 1919, the Maxwell distribution of silver beams, which were evaporated from the melting point. And then they have a mean velocity equivalent to 50 atomic units momentum. And Otto Stern realized that he can use his beam to collimate these beams to very, very narrow beams. When they come off the oven, they go in all directions. But when you collimate it by different steps, you get beams with a momentum resolution at this time already of 0.2 atomic unit. Also below at the atomic value. And this corresponded at this time for the silver team for an angular resolution of 1 microelectron volt. This was far better than at this time photon measurements could do. And it's indicated here how simply it works. You just bring your collimated beam. Here's one atom coming, deflected by a field, and you measure on the detector the deflection angle, and you get then the transverse momentum. This is a picture of the two guys who did then later the Stern-Galler experiment with that. Otto Stern taking this picture 1920 in Frankfurt, and Walter Gerlach. And this was a Frankfurt faculty at this time with several famous people: Otto Stern, Walter Gerlach, Max Born, Alfred Landé, and Max von Lauer had just left for Berlin. Okay, here you see the principle of the Stern-Galler experiment. They have the oven, then the collimation part, and then the magnet and the detector. And the whole apparatus had just the length of a pencil. And with this, here's a picture in the middle of the big magnet. And with this, here you see on the left side the photo when you have just the vertical aperture without any magnetic field. And then in the other case, if you switch on the magnetic field, say source is splitting. And as I mentioned before, the resolution here is 0.1 atomic unit in transverse direction. And this is approximately 1 microelectron volt energy resolution at this time. Compared to that, the Zeeman splitting here of this line is 50 microelectron volts. That means the Stern got a resolution 50 times better than you could get with on the spectroscopic side. Now you can extend this to the so-called continuous Stern-Gerlach effect. That is, apply this effect in traps. And okay, we all know several Nobel Prizes have been awarded for that. And I will just show you beautiful work of Klaus Blaum and Günter Werth, which is published recently and will be published in the near future. And they have built a wonderful trap, which is working now in Heidelberg. And you see here on the left side, the part where in the trap system, the ions are prepared, also highly charged ions, and then they are moved to the part in the trap where the measurement is performed. And inside the trap, you have an excellent vacuum of 10 to the minus 16 millibar and so on, and a fantastic cooling. And then you can follow the particle motion that is indicated here. We know it from the trap motion. There are several oscillations. And that means the outer field are just balanced with the actual momentum of the particle in the trap. And when the measurement takes a second, then you have an infinitely long trajectory and thus also a fantastic momentum or a fantastic mass resolution. And data are published about 2-3 years ago, which precision on the 10 to the minus 11 level. And recently, they have now improved the system dramatically, nearly by a factor 100. First, they use position-sensitive detectors to detect the ejected ions. This provides the phase measurement and thus a precision on the 10⁻12 level. And very, very recently, they were also able to cool by electronic methods the axial motion, which they could not cool so far in the trap. And very soon they will approach 10⁻13 precision. And this is equivalent for the ions of 100 microelectron volt energy resolution. That means if you perform a lamp shift measurement, you should weight the ion in the electronic state. You get a fantastic resolution. Even you have to measure the whole mass of the stored ion. Okay. I have no feeling how fast I am, but hopefully fast enough.
You're on 7 minutes.
Because I'm already nearly through, but it doesn't matter. Okay. Now, Stern was not able to use electronic detectors. Klaus Blaum and Wert in the trap use electronic detectors, but they use still single particles. And now you can extend the momentum measurement to coincidence technique. And if you get very high momentum resolution, you have completely new fields which you can explore. You can explore the secrets in reactive dynamics on a very, very high resolution level in energy and in momentum. And if you detect several particles in coincidence, you are even able to measure relative time differences on the 1 attosecond or even 10 septosecond level. I think Rainer Dörner will present for the septosecond level measurement some data in his talk. And okay, for example, with a cold rimmed reaction microscope, you can do that. And the typical momentum resolution is 10⁻² atomic units. But if you fight, you can even get better. That means you can reach for ions energy resolutions practically nearly 10 nanoelectron volts, which is a very, very high energy resolution. And the method is very simple. I have not to explain it. You have here on the left side, the projectile hits the supersonic cooled gas jet. Then you get free electrons, charged ions, and you project all charged particles on position-sensitive detectors. And measuring the position on the detector and the time of flight, you can reconstruct all momenta with high resolution. And in this picture, the whole apparatus is shown. On one side is the electron detector, the other is the ion detector. And because of the negative and positive charge, both are going to opposite side. And you get with very high coincidence efficiency, practically all particles in coincidence. I will select one experiment which was already performed in the 90s, but it's not really recognized by the atomic physics community. And the question was, but we only knew it later, the so-called off-shell, the virtual contributions in states, which are normally indirectly measured by the lamp shift measurement, are they real? Can they be separated by momentum measurement by coincidence methods? And normally, if you calculate the helium ground state, you have about nearly 99% contribution of the S² state, so on-shell state, but you have about 1.5 contribution of the so-called off-shell state, like P², D², and so on. And as I already said, these contributions are indirectly be measured and then determined by comparison with theory by lamp shift measurements. But okay, I will show you that we can resolve and separate this contribution and project them in the real world and see them by coincidence technique. We have done this measurement in the 90s. by investigation of the transfer ionization process in 1 MeV proton on helium collisions, where the proton captured 1 electron at very large impact parameter, and then at large impact parameter at high velocity. These are mainly these virtual off-shell contributions. And that means when you capture from the p square or d square state, the other electron cannot be bound due to angular momentum conservation. It's immediately emitted. And the purpose of this experiment was to show nicely the existence of the Thomas process. This is indicated here in the small figure. The proton knocks an electron, and under a certain well-defined angle, a second electron is knocked out by the first electron, and then the projectile can capture 1 electron. If the electron is then knocked forward with the same velocity, and the second electron is emitted under 90 degrees with the projectile velocity. And the second process is a Brinkmann-Kramer process, which can also occur, but then the electron which is captured has to move at this moment at large distances already with the projectile velocity. That is more or less a resonant velocity capture. And here our velocity is 6.4 atomic units. That's extremely fast. You barely find electrons in the helium ground state at far distances of this velocity. This can be only off-shell virtual contributions. And okay, we have performed this experiment, and now I show you the momentum plot of the measured recall ion only. And we measure here in inverse kinematics. Yeah, I'm immediately through. And then here the recall momentum is plotted. Also, there's a 0 line. Forward, backward, and left and right. To the right side, the proton is captured. And then we see that the recoil, in the case of the Thomas process, is only observer and remains nearly at 0. But to our surprise, we found a second maximum here, where the recoil is scattered backward. And when we analyzed this peak, we found that this contribution, in this case, the second electron is also always scattered backward under nearly 135 degrees. Also, the first electron was captured with a projectile velocity. That means both electrons carried about an energy of nearly 600-700 electron volt in the helium ground state at far distance. And the distance between these two peaks is only 10 milli-electron volt. That means in a 1 MeV collision, using the inverse kinematics, we were able to measure or to distinguish energy loss channels which were separated only by 10 milli-electron volt. That's an energy or momentum resolution compared to the projectile of the level of 10 to the minus 8. And okay, now we looked more differential to this data, and here are plotted for 3 different projectile scattering angle given in 0.05 millirad, 0.25 and 0.45 millirad. And then we choose one separate second electron energy. And then you see here, when you compare the red data with the calculation, that the S square contribution should give a flat angular dependence, which is in clear disagreement with the data. And the P square are in perfect agreement with the measured data. That means we were really able to separate by coincidence this really existing virtual contribution. Also the P square are really existing in the helium ground state, and you can distinguish them and separate them by this method. Okay, that's the end of the talk. Dear Steve, again, in spite of Corona pandemic, I wish that we have soon again the chance to meet anywhere in the world, Australia or where it is. And the whole, this picture shows the whole Coldreams community, the central part, I must say. There are today many people, but they all congratulate you heartily to your birthday. That was my talk.
Thank you very much, Horace. Thank you. Steve, did you want to say something?
Yeah, just vielen Dank, mein Freund. Thank you, my friend.
Thank you, Steve. So thank you, Horst. Very nice presentation. I think I like the picture as well of the Coltrane's community. I know Robert and Joachim a little bit. So do we have any comments or questions?
Maybe I can make a comment to that, what you said. Many people have told us in the 80s, in the 90s, and later that they had similar idea to use cold rims, but they never thought that it's working. It cannot work. That was the idea. But Steve, when I discussed with him all this crazy idea, we certainly discussed it several times. He always gave us motivation to continue, and that's very important for us.
That's a running theme of the week. Motivation for lots of people in the interactions with Steve. And so I think many you have impacted many people, Steve, that you haven't published with.
Right.
I think is the message which is coming through this week. At this stage, if there are no comments or questions, then I think it remains to thank all 9 speakers in a marathon session. Thanks to everybody who spoke today. I'm going to hand over to Pranawa, who probably wants to say something.
Well, thank you very much, John, for chairing the session, and also Anatoly, who helped us put this session together. And I think we have had a great session. So thanks to all the speakers, and especially to John for conducting it so marvelously. And there were great talks. So we are going to have one more session, which will be same time tomorrow. And yes.
Okay. Yeah, okay, you finish. I just want to add one line.
Yeah. So the session 5 will be same time tomorrow, and it will be on interaction of atoms and molecules with lasers. And Professor Kiyoshi Oida would chair it, and Professor John Costello would co-chair it. So we are ready for tomorrow, and please do join tomorrow. Well, there could be some reason why this could be kept as a surprise, but I would rather spell it out, because I want all of you to know that in advance, so that you make sure that you participate in tomorrow's event. At the end of the scientific session, we will have a small felicitation for Steve, and some of his colleagues and friends will be speaking at it, even though it will be a very brief and short session. And we wanted to keep it as a surprise, but then I also want everybody to know it in advance, not to miss it. So thank you all. We'll look forward to have you tomorrow. Lokesh, you wanted to say something?
I just wanted to add a sentence that it is true that even I do not have actually a direct collaboration or paper with him, but we keep meeting in ECPICS, all ECPICS, and I am sure if I search my computer, there are very nice photos with him. And particularly, I think we are in Australia 2017, and Deauville, I don't remember whether he was there, but we keep meeting in our conferences, and certainly we'll be happy to meet soon after again.
Amen to that.
Yes. Look forward to meet you again. Thank you so much.
Is there any other comment from anyone?
See you tomorrow.
Yes, Kiyoshi.
Yes, see you tomorrow. Over to Kiyoshi.
Yes. Kiyoshi will be Kiyoshi will be our session chair tomorrow. Yeah, and for Anatoly, it is already late, so I think let us close the session and we will meet tomorrow. Okay, goodbye.
Okay, thank you, Pranava. Thanks,
Bye, everybody.
Bye.
Thanks,
Goodbye.
Bye-bye.
Goodbye.
Bye-bye. Take care.